Hello everyone, welcome. So in this video we'll be discussing Kuramoto-type oscillators with nonlinear feedback. Now that might sound like a jargon to you, but I'll try to explain this concept, this topic in a very simple way without compromising the rigor, obviously, because I know this is YouTube, so I'm not presenting to a technical audience right now, but at the same time I think this is a very important model, the Kuramoto model, in especially in modern research, interdisciplinary research. Yeah, of course, maybe not all of you are scientists or researchers, or not all of you. This is not relevant for all of you, but I'm assuming that if you choose to watch this video, it's probably is relevant for you. So this was part of a project I carried out in the summer, as you can see, June 2025, under the supervision of Professor Sitabhra Sinha at the Institute of Mathematical Sciences, Chennai, a part of a summer research internship. So exploring synchronized oscillations in Kuramoto-type oscillators with nonlinear feedback. Okay, first of all, let's start with a very broad, very basic question before we move into the technicalities. I would, as much as I would have loved to talk about the broad fundamental questions throughout the entire video, throughout the entire presentation, but unfortunately, the topic in a particular presentation, we have to focus on a very specific, very specialized topic. That's the way progress is done. Otherwise, we'll be moving in circles. But at the same time, I would try to, at times connect the topic we're discussing to the big picture whenever and wherever possible. So first of all, ordered complexity is a fortunate product of random processes. Now, some of you probably know this already because I keep saying this. It's kind of like a mantra of mine almost. I have been saying this on in my writings, in my videos, on my website for the last 3 or 4 years, if I remember correctly. Now, the first question is from a very general perspective. How can order arise from randomness? Because the way these terms are defined to the common people, it might seem that order and randomness are at odds, like they are, I should say, one opposes the other. Now, that's not always true because at the same time, yeah, of course, they are kind of opposite. Order and randomness are kind of opposite. But at the same time, in the field of, in the science of complex systems, it's often opposite tendencies or opposite effects that give rise to something beautiful, something stable, something complex. So first let's look at, this is not really relevant to what we'll be discussing, but still I devoted one slide to this because this is a very good example. And it's the Sierpinski triangle. So this is a fractal basically. What do I mean by fractal in very simple terms is that this does not depend on the scale. Just look at this picture. If you look at the entire picture, just follow my cursor. If you look at this entire triangle, you see that you see some pattern. Now if you look just in this smaller triangle at the top, or this one, you see, or this one, you see the same pattern. So basically this pattern repeats infinitely, and there's a very simple deterministic way to generate this pattern. That's why see, this can also be generated deterministically. You start with a triangle, equilateral triangle, a solid triangle. So initially you don't have any of these patterns, just a solid triangle. Then you just mark the three midpoints of the three sides of the triangle. So this is an equilateral triangle. This is the midpoint of this edge. This is the midpoint of this edge, and this is the midpoint of this edge. So you mark these 3 points and join them. So you get an inverted equilateral triangle. And by doing this, you divide the original triangle into three smaller equilateral triangle facing upwards. I mean, aligned in the same direction. You see what I mean? So this is one step, let's call it. Now you repeat this for these three triangles you have produced, and you keep repeating this for the subsequent triangles you will have, and you keep doing this iteratively for, as for a large number of times, for infinite number of times ideally. Then you get this pattern. So why do I call it a fractal? Because it doesn't depend on the scale, on the length scale, because it doesn't matter whether you're looking at this triangle or this or even the smaller ones. In essence, it's the same pattern because it goes on to infinity, at least mathematically, right? Also, you can think about it, it's a very good way to think about this. It has a fractional dimension. So what do I mean by dimension? Usually we know that things can be, let's say, one dimensional, two dimensional, three dimensional, blah blah blah, right? So these are whole numbers, integers. You usually, if I suddenly just a second, I'm sorry, yeah, if I suddenly claim that the dimension of that object is 1.5, that might sound like I've gone mad or something. But yeah, fractals can have fractional dimensions. So without going into mathematics, just if you think about it, is this really a two-dimensional figure? Yeah, of course it is on a two-dimensional screen, but it's not solid. I mean, a solid triangle is a 2D shape on a lying on a 2D plane. So it has a I mean, it's in a way it's on a 2D plane. But this is really not a two-dimensional object, because you keep taking parts of it. First of all, you remove this, then you do this, and then you keep doing this. At the end of the day, you almost have just some lines. You don't have any area. By two dimension, usually we mean area, right? There should be some surface, there should be some area for us to call is two dimensional. But what's the area of this? You keep just taking things off, and ultimately all you have is are just empty, like these white regions. And the blue regions, they're very intricate, but at the same time they're just lines, they're not really areas. But at the same time, is it just can this entire figure be regarded as a one-dimensional, let's say one-dimensional line? Not really, because if we talk about a circle, not a solid circle, just the circumference, that is in a way one-dimensional. Because if you just cut the circle at a point and open it, let's say unfold it, you get a line. So this is, but this thing goes on infinitely. So this is, let's call it an infinite one-dimensional curve. So since it's infinite, just intuitively you can see that it has a dimension which is greater than 1 but also less than 2. So it lies somewhere between 1 and 2. So it has a fractional dimension. This was just a way to, like, intuitively, but actually you can also do it the mathematical way. This is not really relevant, so I'll just briefly mention it. If you because it would have been better if I had figures and stuff to show, but I don't have that for this one, because like I said, this is not really relevant for the Kuramoto oscillators. But I'm still mentioning this to you. If you don't get it, that's totally fine. So for instance, we call a line one-dimensional. Why? The exact mathematical way. So let's say we have a line here, and we divide the line into two equal halves. Let's say we'll divide the line segment into two equal halves. We just mark the midpoint of the line, and we have two equal line segments, two equal halves. So we divided the line into two equal halves. So how many the smaller parts? I mean, we divided the line into two equal parts. So these are the smaller parts. Let's call them sublines. Yeah. So how many sublines do you need to get back the original line? You need two of them, right? You divide it into two parts. You just join the two and you get the original line. So it's like, you'll see why I say this, because this is a very helpful way to think about dimensions. So you scaled the original line by half, 1/2, right? You divide it into half. So I mean, how many parts you divided into? You divided into two parts. So the formula, let's call it a formula. So the formula is 2 raised to the power x is equal to the number of smaller parts you need to get back the original line. So in this case, it's 2. So 2 raised to the power x is 2. So x has to be 1, and that's why a line is one-dimensional. This x is the dimension, basically. Similarly, if we have a square, a perfect square, so a square is a two-dimensional object, right? So why is it two-dimensional? Now, if I divide this, let's say we have a square here instead of a triangle. So you divide the side, all the four sides of the square into half. So you divide this side into half, just the midpoint, and you do this for all the four sides of the square, and you join all the parts. So now you have 4 smaller squares. I mean, this is pretty easy to visualize, right? You have 4 smaller squares right now. So you divided each side into 2 equal parts, but you need 4 smaller squares to get back the original square. That means 2 to the power x is 4 this time, which means x has to be 2, right? But in this case, you divided one side, each side of the original equilateral triangle into 2 parts. So that's 2 raised to the power x has to be, it has to be 3, because you can see you need 1, 2, and 3 such smaller triangles to get back the full original triangle. So if 2 raised to the power x is 3, I mean, of course, you can just take the logarithm of both sides and find the value of x. It's if I remember correctly, it's 1.5, 1.6, or I don't remember exactly, but it's a number between 1 and 2. So it's a fraction. Now the point is that, so we started with the question, how can order arise from randomness? Well, there's a very good way to generate this pattern. Other than what I said, it can also be generated deterministically. You start with a triangle and you mark the midpoints and you keep doing this. That's a very clean way to do this, because that's deterministic. There is no randomness. But at the same time, it's very interesting. It's called the chaos game. We can generate this randomly, stochastically. By stochastically, I simply mean that there is some randomness in this second process. But it's also a very valid way to generate this pattern. So what you do is that I have not described it here because again this is not the main point of this presentation, but yeah, as I'll just briefly mention this to you. So you just mark the three vertices of the equilateral triangle. So you just have 3 points A, B, C, let's call them A, B, C, and you roll a die. So you can have 6 outcomes, 1, 2, 3, 4, 5 and 6, and assuming it's an unbiased die, the probability of each outcome is 1 over 6 in one throw, right? So you start with any point, let's say any random point. So if you get a 1 or a 2, that's a probability of 2 over 6, right? Because the probability of getting 1 in a throw is 1 over 6, and that of getting a 2 in a throw is also 1 over 6. So you have 2 times 1 over 6. So if you have either 1 or 2 in as your outcome after you throw the die, you you just mark the point which is the midpoint of the line segment joining the initial point to point A. I'll go once again. So let's say your initial point is here, let's say here, and you get either a 1 or a 2. So you don't draw the line, but in your imagination you just draw the line from your initial point to A, and you mark the point, the midpoint of this line segment. This one you mark. Now let's say you get 1 or 2 again. So now this midpoint you mark, that becomes your working point. So from there you again draw the line to A and mark the midpoint, and you keep doing this. So if you get 1 or 2, you just do this with A. Now let's say you get a 3 or a 4, then from the last working point you mark the midpoint of the line segment joining the last working point to this second vertex B, and if you get a 5 or a 6, you do it with C. So basically all the points are equally likely to be chosen because the probability is 2 over 3, 2 over 3 and 2 over 6, 2 over 6 and 2 over 6. But there is some randomness. The rules are deterministic, and if you do this for a large number of trials, you will get this pattern. So the rules and outcome, they are deterministic, but the randomness is encoded in the rule, in the process, because when you throw a die, of course it's over a very large number of throws, there is actually no randomness because it's basically the law of large numbers. If you throw a dice a large number of times, then the probability of getting 1 is indeed 1 over 6. It will converge to 1 over 6, right? It's an invariant distribution. But if you throw a dice, let's say for 10 times or something, let's say throw a die 60 times. So then 60 is not a very large number. So then it's very unlikely that you get exactly 10 times you get 1, 10 times you get 2, 10 times 3, 10 times 4, 10 times 5 and 10 times 6. The probability is exactly 1 over 6 for each outcome is very unlikely. So it can fluctuate. So there is a little bit of randomness in the rule. Although over arbitrarily large time periods, technically speaking, it's not randomness in that sense. So this was like a good thought experiment, and the point of this was to just for you to let's say appreciate that there was a randomness, but how can order arise from randomness? So if I am more honest with you guys, this is not really randomness. This is a randomness that decays with time, decays as we increase the number of trials, number of steps. But it still is randomness initially. But if we keep doing this is like somewhat similar to like the robustness of the algorithm in a way. If you keep doing this, you always get back this pattern. So that's rules, that's order. Now, why study complex systems? Before we start discussing on Kuramoto or any of that, why study complex systems at all? Well, so in many real life, let's say systems and complex phenomena, we have emergent properties, which means properties that we cannot understand just by studying the parts. So it's kind of like a greater than the sum. So if you have 5 parts and you build a system by connecting the 5 parts, but the system behaves in such a way that you cannot explain the behavior just by studying the parts individually. For instance, water, the most common example. I myself have used this example in the past a lot of times, and it works, by the way. So one water molecule, just hypothetically imagine if I could give you one water molecule, one H2O molecule. Is it really wet? If you just hold one, of course you cannot hold it, it's very tiny, but for instance, let's say if you could actually touch and feel one H2O molecule, just 2 hydrogen bonded with an oxygen. Would you feel wet? You will not. But water as a whole, it feels wet, right? So this wetness is kind of like an emergent property. It's true. This example, for instance, about the snowflakes. So if you really want to explain everything, like how the let's say the triple point of water, the ice, water vapor, you cannot explain everything just by focusing on a single H2O molecule. Although in principle, ice, water and water vapor, they're all made up of H2O molecules. But the arrangement of H2O molecules, that's different in ice than in water, for instance. And that is a very crucial difference. That changes the behavior. Fundamentally, that changes the behavior of ice and water, for example. So, but to look at the arrangement, you have to look at the whole. You cannot just look at... if you want to see how the H2O molecules are arranged in the entire structure, in the entire system, you cannot just focus on a single H2O molecule. That will give you no information about that. And so this is a good example about downward causation. Okay, before that, weak emergence or strong emergence. So this is basically something which, I mean, it's still not established. I mean, there are opinions, diverging opinions on this. Some people say that, so what do you mean by weak emergence? Weak emergence means that, well, basically these new properties, they are emergent, they appear to be emergent to us, but that's only because we don't this system is very complex. It's made up of, let's say, millions or billions or trillions of parts, and it's in principle it's not possible for us, even using computational techniques, numerical techniques, in principle it's not possible for us to really see how these patterns or how these emergent properties actually arise from the parts. It's not possible for us to see. So we just let's say we focus on a coarse grained description. So that's why they are emergent but weakly emergent, because in principle maybe it's still possible to understand the system just by studying the parts individually, but just we don't have enough computational power or whatever. But the guys who believe in strong emergence, and by the way, it's not really weak emergence versus strong emergence. I mean, there can be some systems which are weakly emergent, some systems which are strongly emergent. It's not necessary that one of them is true and the other has to be false. It's not like that. But yeah, the idea of strong emergence is that, well, the emergent properties are fundamentally new properties. So even if hypothetically you had infinite amount of computational or mathematical power and you actually tried to understand the system just from by its parts, even then you would not be able to explain these strongly emergent properties. Downward causation, well, the idea of upward causation is pretty obvious. Like, the parts affect the whole. I mean, if you are made up of a large number of cells, and if one of your cell malfunctions in a critical way, that can give rise to, let's for instance, cancer, and that can affect your whole. That's very obvious, right? But downward causation is the opposite idea, that can the whole also affect the parts. And yeah, I mean, maybe it can in some systems. For instance, I'm not sure if this can be cited as evidence in favor of downward causation, but this sure is a very good example, very good illustration of what I mean by this. Snowflake. The basic constraint of snowflake is that it always has a six-fold symmetry. Now, snowflakes can be like, the snowflakes come in different shapes. For instance, these are all snowflakes, but they have like different shapes. This is the hexagonal plate shape. This is stellar plate. This is stellar dendrite. This is fern-like stellar dendrite. I think this is the most popular, anyway, popular one. But these are all basically snowflakes, and you see they all have a six-fold symmetry. Now, what I mean by this is that, well, in a circle, I mean, if you start from here and you rotate, I mean, you complete one full revolution, you come back here, is basically you move 360 degrees, right? So you divide 360 degrees into 6 equal parts, because that's what I mean by six-fold symmetry. N-fold symmetry means 360 by n, basically. So 360 by 6 is 60 degree. So by six-fold symmetry, I mean that if you rotate this by 60 degrees, then the orientation of the figure as a whole does not change. That's why it's symmetric. So it's true, because this is kind of like a hexagon. So if you rotate by 60 degrees, this this comes here and this comes here. I mean, basically the system has rotated by 60 degrees, but it still looks the same. And that holds true for all of this, right? So snowflakes must respect the six-fold symmetry. So why do I say that this is an example of the whole affecting the parts? Well, first of all, the snowflakes are built from the parts, right, from the molecules. But at the same time, once they're built, this six-fold symmetry is a constraint on the whole. This is not a constraint on the parts. It's a constraint on the whole, that once the whole structure is formed, it must obey, it must respect six-fold symmetry. And that constraint, actually, it's an important constraint which does affect the parts, because the molecules, the parts cannot arrange themselves in such a way that does not respect six-fold symmetry. For instance, you see these particular arrangements, there are many other possible arrangements of these molecules, but we don't observe them in nature because they don't respect six-fold symmetry in a way. And now the comment I was making about opposing effects or competing effects. Well, interesting stuff happens when two opposing forces interact. The best example probably, since the guys like us who are like studying biological systems, free energy, I mean entropy versus energy. There's this battle between energy versus entropy. So at low temperatures, things want to be things have a tendency of remaining ordered, because that minimizes the internal energy, just like a stable minima. And at high temperatures, entropy has the dominant effect. Things want to explore the configuration space uniformly, and they want to they tend towards a more random configuration. Now, if that's technical, that's not the point of this presentation, so never mind. But it's a very important idea, that when you have two opposing forces, entropy and energy are kind of like opposing forces, but The balance between energy and entropy is everything. I mean, that's what keeps the biological system, biological systems, or any many other complex systems, not just biological systems, in keep it functioning basically. Some less obvious, I mean, let's say some less formal examples. Well, music, predictability versus unpredictability. So music, well, if I just do a periodic sound, like for instance a sound like just every 2 seconds I just beat the drum once, but there is no other music, no other melody, just a periodic sound, so that's completely predictable, and that's not music, that's boring. Now if I talk about complete unpredictability, for instance you go out on the, I don't know, in the marketplace or something, and it's chaos everywhere, people are randomly speaking, shouting and whatever, that's also not music. So what makes us love music? Because music is a balance between predictability and unpredictability. At least the first time you're hearing a song, it's unpredictable, you don't know because you're listening to it for the first time. But at the same time there are some predictability. Once you have listened to the first verse, you know that okay, maybe this the melody would not change by a significant amount. Maybe after the first drop there will be a second drop, so there will be a similar build up, similar verses, or let's say the chorus might repeat. You see what I'm getting at? There is a balance between predictability and unpredictability in music, and that's what makes it beautiful. Universe, well, of course, gravity versus expansion. The universe as a whole is expanding, and locally gravity, due to gravity, locally clusters, galaxies and stars and everything can form, otherwise we wouldn't be here. Animals, or I mean any social creature basically. Autonomy versus interaction. Humans, look at humans for instance. We want autonomy, we want to, like, always have an individuality, like we want to, sometimes we want to act like we are supreme, we are, you see what I'm getting at? We have our individual self respect or ego. It's not, it's more like ego, what I mean to say. But at the same time we also interact when required. We also interact with people because we're social creatures, we cannot really live in isolation. So it's a balance between interaction and autonomy. Both are important, both are required for to live a proper, to live in society basically. Both are required. It's not like which is good and which is bad. And we already looked at the Sierpinski triangle, rules versus randomness. So the Kuramoto model is basically, it's a nonlinear differential equation. So basically it's nonlinear dynamics. Nonlinear dynamics is basically the study of complex nonlinear systems. Everything around you is basically nonlinear in real life. In physics we often linearize things, and even linear algebra is very useful. It has in quantum mechanics framework is entirely based on linear algebra and everything. So I'm not saying it's not useful, but at the same time, uh, linear is very like if we assume a system is linear, that means it's boring, it's predictable. In real life things are nonlinear. For instance, you see what I mean by nonlinear? Things can speed up and slow down basically, if I put it in very rough terms. And there are two very good approaches to do nonlinear dynamics. One is using differential equations, which is what we will be doing in this presentation. The other is using difference equation. Now differential equations are useful when we deal with a continuous, for instance in continuous time, for example. Like let's say we use the master equation often. So master equation is basically a way to model this continuous processes, differential equations. Continuous time Markov chain, for example, it's used, you can model it using a master equation. Nonlinear coupled oscillators, that's what we'll be looking at. Difference equations, this is just an example, but we will not be discussing this in this presentation, of course. So it's more useful when we have discrete systems like the logistic map. Oh, I included one slide anyway, so just to give you the idea. But yeah, from the next slide we'll be moving on to our main topic. So all this was basically just yeah. So this is a difference equation. You see there is no continuous time, there is no derivative or differential term. It's not a differential equation, it's what we call a difference equation. I mean, you can actually this n is a, I'm sorry. So this n is actually a discrete basis. For instance, n can be 0, n can be 1, n can be 2, and so on, n plus 1. So basically it's discrete basis. Now you can turn this into a continuous basis, and in that case you will have to deal with a differential equation basically. So this equation is a very good equation, which and it's used to model population dynamics, for example. So this is the plot of x versus r. So r is this r, it's an order parameter here basically. It's a kind of like a control parameter. I'll just briefly explain this to you. So x basically, you can think of it as if we are studying populations, then I mean it could be something else as well. It could, for instance, it could be something like concentration also, but here we are talking about population. So x is the number of species, yeah, in a way concentration of the population. So xn is the population at time step n. So let's say n is now present, so n plus 1 is after one time step. So depends on how you're modeling, it could be after 1 year or after 1 month or whatever. So n plus 1 is the future, next time step. And since it's a discrete model, you really can't speak about what happens between n and n plus 1. After n, we have n plus 1, then we have n plus 2, and so on. So that in the next step, what happens is that depends on r, which is basically the rate of growth in a way. You can use it to model the rate of growth. Xn times 1 minus xn. So you see why this is useful when in modeling population, because xn is the current population. So if you have a lot of species right now, that means this is a big number. So this will also tend to increase this, because if you have a lot of species right now, they will reproduce, and there is a probability, there is a good chance of having a lot of species in the next time step as well. I mean, in the future as well. But at the same time, it's not really linear. That's why I say it's non-linear. See, if you just multiply the equation, you have rxn minus rxn squared. So you have a quadratic term. It's squared, non-linear in xn. And this non-linearity is important because if xn increases too much, then you see the second term dominates, rxn and rxn squared. But if xn is very large number, then xn squared is even huge number, and then you have a negative effect. Because of course, it's not just, I mean, a population cannot go on increasing indefinitely. There is competition for resources. Resources is finite, and food, shelter, everything. So if a population becomes too large, then automatically there is maybe the species start killing each other or something, but yeah, it will come down. So if xn increases too much, then 1 minus xn actually decreases, because it's 1 minus xn. Maybe xn is normalized between 0 and 1 in the inner model. Yeah, so basically, yeah, so what you're plotting here is this x as a function of r. So r is basically the parameter, because we keep increasing r and we see how the system behaves, and this is called a bifurcation, because at this critical value of r, I mean, see, for all values of r less than roughly 3, I mean, in this range, basically the population basically converges to a fixed value. You see, it converges to a fixed value. So if you looked at the time series of x versus t, you will see it converges to a fixed value if your r is less than, I mean, in this region. But in this region, you see the bifurcation. So x basically converges to two values, once this value as well as this value. So in the time series, you will see bifurcations, like you will see fluctuations like this between the population basically fluctuates between two values. And after a certain point, suddenly things become chaotic. This is what's called chaos theory. Actually, chaos theory is also another name for nonlinear dynamics. It's called chaos theory because, yeah, you see, this becomes chaotic. That means for these values of r, you cannot predict where it will be. But at the same time, why I call self-similarity, because there is some self-similarity. I mean, if you keep zooming in, I mean, it's not visible in this picture, but if you actually plot this equation or even look at animations on the internet, you see this roughly this figure, this figure, I mean, I'm sorry, what should I say, this shape, this repeats even at smaller scales, and it's kind of like fractal. It's kind of self-similar in the same way we looked at this. You see what I mean? Okay, but for us, we'll be talking about oscillators and synchronization in this video. Now, internal frequency. So when we are looking at oscillators, first of all, we define an internal frequency. Basically, it's the frequency of the oscillator. Frequency is just 1 over time period. So basically, how long the oscillator takes to oscillate one full revolution, that's the time period, and the reciprocal of that is the frequency. So if the oscillator takes very less time to do this, but it's oscillating very fast, so it has a higher frequency. Like, it's a higher frequency means it's doing this very fast, and lower frequency means it's taking a larger period of time to complete one revolution. And yeah, we'll be talking about the angular frequency, omega, basically. Yeah, so it's the same thing. You can think about an oscillator just as a, let's say, as a sinusoidal curve, or also as a circle. You can just map it on the phase circle, basically. So because the phase is between 0 and 2 pi, we'll look at the phase circle anyway, so don't worry about it too much right now. It comes after a few slides. Now, a group of oscillators are called to be synchronized, since we'll be talking so much about synchronization. So what is synchronization? Well, a group of oscillators are synchronized if they have a constant phase difference. Now, I don't mean constant phase, by the way, just constant phase difference. We call it phase locking. So what is the phase of the oscillator? It's just, I should say, the angle. For instance, if I'm at 30 degrees, so that's my phase right now. On the phase circle, it's 0, this is 30 degrees, this is 90 degrees, and I'm sorry, so on. You come back to 2 pi, which is again equivalent to 0 degrees. And I'm doing this oscillation. So my phase is just my theta, my angle. It's, let's say my phase is 30 degree and your phase is 60 degree. Are we synchronized? Well, if I keep oscillating but at a constant frequency, that means of course my angle is changing, but the phase difference between us is not. Of course, right now I'm at 30 degree and I keep oscillating. So after some time I am at 60 degree, and by that time you are at 90 degree if the difference is constant, or maybe, so that's when we can say that we are synchronized. But for instance, you are moving at a faster speed than me. So right now I am at 30 degree, you are at 60 degree. The phase difference between us is 30 degrees. 60 minus 30 is 30. But let's say you move very fast. So when I have reached 60 degree, you have reached, let's say, 120 degree. So right now the phase difference between us is 120 minus 60, which is 60 degree. So the phase difference between us is not constant, it's changing. It was 30 degree, then it becomes 60 degree. That means we are not synchronized. But if the phase difference is constant, although we are moving, of course, we are not fixed. Like when I'm at 30, we're at 60. When I'm at 60, we're at 90. When I'm at 90, we're at 120. So basically, always the phase difference is 30 between us. Then we can see that we have phase locked, and that's a kind of synchronization. So synchronization is observed in cardiac muscle cells in the heart, for instance, that aid in coordinated contraction, in the firing of neurons, in the flashing patterns in some species of fireflies, etc. So it's observed in a lot of places in nature. So it seems like it's a mechanism which is used by nature, and it's very, it's also, it has other applications in engineering also. For instance, it's not just, so it's a very useful model. This model of coupled oscillators, Kuramoto models as well. Mm. So this is the basic equation of the Kuramoto model. So here we have theta. Theta is the phase, and you have n number of oscillators, for instance. N could be, let's say, 100 oscillators, n is 100, for instance. It could be any number. So I is an index which runs from 1 to n. So this theta I is the phase of the oscillator I. So this equation is a local equation in the sense that this holds true for every oscillator in the system, but it's the equation for a single oscillator. So let's say you have 10 oscillators. That means in reality you have 10 such equations, but all of them have the exact same mathematical form. So that's this form. So you just write it once and you say that this index I runs from 1 to 10. So theta I is the phase of the oscillator. So let's say right now I'm at 30 degree. That means my theta I is 30 degree. And of course this is changing with times because I'm oscillating. So how is it changing? That's the left hand side, d theta I dt, the time derivative of theta I, the time evolution of theta I. So how am I moving on the circle? How my phase is changing? That depends on a lot of factors. First of all, that depends on my own frequency. This is my internal frequency. I am I, and this is also depends on I, omega I. So if I have a very large frequency, of course, I am moving very fast. So that means, that's why you see there's a positive sign. So that means if omega I is large, then d theta dt also increases because it's a positive sign, which kind of makes sense. It should, right? If I have a small frequency, then well, I'm moving slowly. And this term is the coupling term. So basically what is K here? I'm sorry. So what is K here? K is the capital K. This is the coupling. This is basically called the coupling strength. So here we assume that they are coupled oscillators. So let's say we have n oscillators, and these n oscillators are not really independent in the sense that they are coupled. Let's say we have 10 people who are holding hands instead of, let's say, 10 people who are just moving randomly and independently of each other. So they're holding hands. So how strongly are they holding hands? That is being determined by K. And yeah, for simplicity, we say that the strength is the same for all oscillators. So let's say there are 10 person, and if they're all holding hands, they are all holding hands with the same strength. So between any two person, you pick any two person and they're holding hand with the same strength. Of course, you can play with these parameters if you want a more nuanced model. But yeah, right now we're just understanding the basic, just the way it's defined, first of all. Then we will look at simulations and stuff. And we normalize this strength by Ki. So Ki is the number of neighbors, number of oscillators that the ith oscillator is directly connected with. Let's say there are 100 people in the network, but not everyone is connected to everyone else. Let's say I am holding hand with 2 people, someone else is holding hand with 2 people. It's not necessary that I am holding hand with all the 100 people, but still I am part of the network, and the network as a whole has 100 people. So yeah, for humans, we cannot really hold hands with more than 2 people because we have 2 hands. The idea is that in oscillators there is no such limit. So for instance, the oscillator I has, let's say, 5 nearest neighbors. So it's directly connected to 5 oscillators, but there are many other oscillators which the oscillator I is not directly connected to. So this Ki would be 5 in that case because it's the number of nearest neighbors. Why do we divide K by Ki? Because K is the coupling strength. So if you have 5 connections, then you actually have 5 times K. K is the coupling strength of one connection. But that means you unrealistically kind of increase the connection, because in the entire network it should normalize, because by normalize I mean that from each node or from each oscillator it should normalize it, because if I have 5 connections, then my connection strength is distributed equally among the 5 connections, Distributed equal is an assumption. In case of real humans, of course, it's not like that. If I have 5 friends, it's not necessary that I will like 5 of them with the equal intensity or something like that. But yeah, in our case, we're not talking about humans, for instance. So you see where I'm getting at. If my connection strength is finite and fixed and constant for all oscillators, for all humans, let's just to use an analogy. But if I have to connect with 5 people, I have to divide my strength, my connection strength, into 5 equal parts. So that's why we are doing this. But if I have to connect with just 2 people, then it gets divided into 2 equal parts, and so on, just to normalize. And this is the summation. So this sum runs over the number of, basically it's just the number of nearest neighbor, yeah, nothing else. So it just runs over j, where j is the number of nearest neighbor. So j is not basically, yeah, if you say that all the oscillators are connected to all oscillators, let's say, then j is basically all the oscillators except I. But that's not really true, because that's not necessarily true, because you can have, like I said, you can have 100 oscillator network, but oscillator I maybe is directly connected to only 10 oscillators. So then you only sum over those 10, because the others won't have any direct effect on I. And what is this term? So of course this is a nonlinear equation, but first of all, basically sine is nonlinear, and you have, so here our variable is not theta j, our variable is theta I. When we are focusing on the behavior, the phase evolution, I mean the time evolution of the phase of the ith oscillator, so we essentially treat all the theta j's as constant. I mean, we are not really solving for theta j. The differential equation is theta I. But there is theta I in the argument of sine, and sine is a nonlinear function. It's a sinusoidal function. So this is a nonlinear differential equation, right? So sine theta j minus theta I. So why is this term important? First of all, you are summing this over all the nearest neighbor, all the connections of I. So this is basically, if you have 5 connections, you actually have 5 terms. It's a summation for 5 j's. Now let's say I is, so why this term helps in synchronization? See, sine function, 8, synchronization, all of this I've written it here. Why? Because, well, I am connected to, let's say, 5 people, and they are all dancing. We are holding hands, by the way. And they are dancing very, let's say, very energetically, but I am not dancing very energetically. I am like, no, I don't like to dance, let me just keep quiet. But if you're holding hands with 2 people who are jumping like very energetically, then you will also start to move and, start to jump. You see what's happening? The movement of your body is getting synchronized with the movement of their body, because you are holding hands. At the same time, if you are jumping very energetically, but you are holding hands with 2 or 3 people who are very quiet, then, because now it's kind of like the majority wins, because the majority is quiet and you alone are trying to jump, but since they are quiet, they will try to calm you down, like, come on, we don't, like, they will hold you firmly, and after some time you will find it difficult to move your body, and maybe you will also slow down. So your body movements are again getting synchronized with them. So as a whole, the entire network of oscillators is getting synchronized. And why sine theta j minus theta I? So theta I is you and theta j is everyone else. That's why you sum over all the j's. So let's say you are dancing very energetically, but everyone else is quiet. That means theta I is larger than theta j. Basically, you are like, let's say you are at a higher phase in a way. But that means this term is negative. You see, theta I is larger than theta j. That means theta j minus theta I is negative. And sine of anything negative is negative. Right? As a whole, it becomes negative. So this term becomes negative. And on the left hand side, you have the time evolution of theta I. So it has a negative contribution from this term. That means if you alone are dancing energetically and everyone you're connected with are very quiet, that means over time you will also become quiet. That's why it has a negative contribution. But at the same time, if everyone else is energetic, theta j is positive. I mean theta j is greater than theta I. It's not about positive negative. Theta j is greater than theta I. Then this term as a whole is positive and sine is positive, and this term aids synchronization. I mean this term has a positive feedback to theta I. So you also start dancing energetically, because everyone around you, everyone you're holding hands with is dancing energetically. So you see what I'm saying. Now in this presentation, we'll be looking at the same system, but we add an extra term, and it might sound simple, but this actually changes a lot of stuff. We add extra term. This is negative a sine theta I. So we have theta I, which is a variable, and sine is a nonlinear function. So this is a nonlinear feedback. Why do I call feedback? Because it's a negative term, and this is always negative. I mean, a is a constant, it's the damping constant, so it's positive. And sine theta I mean theta is a number between 0 and 2 pi, so sine theta is also always positive. I mean, if you have sine of something negative, that becomes negative, but theta I is by default positive, right? So in this case, you can have negative because it's theta j minus theta I. So this term always kind of, let's say, suppresses the oscillators. In a way, if the oscillator is doing this very fast, it has a negative feedback from this term. It says that, hey, slow down, in a nonlinear way. Nonlinear way because it's like, you see, sine theta. So if theta is very large, then sine theta also becomes 1. I mean, sine theta doesn't scale linearly with theta, right? It does like this. It's kind of like, you see what I mean. So this term basically is an extra nonlinear damping term. It dampens the oscillators. And yeah, this is a good model to study because it's very realistic. In real systems, of course, things don't keep oscillating, because if we don't have this term, all we have this synchronization and this thing, I mean this omega, which is the internal frequency. But in reality, there are often feedback mechanisms to keep things in check, let's say. So for this system of equations, this equation, yeah, if we assume that everything is phase locked, I mean that's an assumption for making these 3 points. These 3 points will only make sense. You will see why. So we're assuming that all the oscillators have a constant phase difference. They don't necessarily have the same phase, but they have a constant phase difference. You see what I mean? Then if omega is less than a, I mean we are looking at a one particular oscillator. So let's say we have fixed the value of I. So now we don't need to write omega I. So if the omega for that ith oscillator is less than a is, let's say, constant throughout the network, then we have two fixed points. And it's possible that there are phase slips before settling at the stable fixed point. Okay, I'll show you the pictures, it will make more sense then. But let me just read through this anyway. If we have omega greater than a, so if that means the internal frequency tells the system to do this very quickly. The higher the frequency, the more faster, the more vigorously the oscillator is oscillating. But a tells it to slow down. So basically it's a competition between omega and a. So if omega is less than a, then this a wins out and the oscillators settle at a fixed point. It cannot continue oscillating, it settles at a fixed point and stays there. But if omega greater than a, it keeps oscillating. It's basically continuous drift scenario. And yeah, in real systems it's always a mix of coupled oscillators with, I mean, in real systems actually omega is not the same for all oscillators, you see. So I mean, of course, that's why we need an index omega I. So let's say some oscillators among all the oscillators has an omega which is less than a, and some oscillators have an omega which is greater than a. So in real systems you can have mix of oscillators with omega less than a as well as omega greater than a. I mean, you can actually tune the mean value of omega. I mean, you have, let's say, 100 oscillators, let's say n oscillators, and so you have a distribution of omega values in the n oscillators, right? So for instance, in our simulations, we'll be drawing omega from a normal distribution and randomly assigning the values to the n oscillators. Okay, we will see that anyway. So right now, let's move on. So you can tune the average value of omega accordingly for a given value of phi. Now in statistical physics, we usually we usually deal with the phase space. We usually do the analysis in the phase space. In classical physics, usually we have I mean to say it's basically it's not really configuration space, by the way. Configuration space is just the in classical dynamics terminology, configuration space is the space with all the generalized coordinates, but you don't have time there. So yeah, it's basically I think it's a good idea to call it real space. Don't think of it as real space like like the space you are in, because you don't have a time axis which you can physically see. I mean, physically it's not like xyz. Basically what I mean by that is that x versus t. So you have position here and you have time here, basically space-time diagram in a way. I think space-time would be a better term than real space, sorry for that. So when you have, let's say, one single particle, you can do the analysis in x versus t. It's easy, right? The slope of the line will give you the velocity dx dt. But in statistical physics, we deal with a large number of systems, and we usually do the analysis in phase space, which is the position versus momentum space. So it's a two-dimensional space, but it's for one particle it's two-dimensional, but it's for n particles it would be I mean, it depends actually. Phase space is a mathematical space, it's not real space, so there is no limit to the number it can be n dimensional in general. It depends also on the number of degrees of freedom of the system. So for instance, if the particle is confined to move only in one dimension, either left or right, then you can say it's two-dimensional for one particle. Otherwise not really. If the particle can move in x, y and z 3 dimensions, then it's six-dimensional. So basically a point on the phase space gives you the microstate, the entire state of the system, because a point on the phase space is basically has coordinates of position comma momentum. So why this simplifies things, because if you know the momentum, you know the velocity, you don't have to find it from the slope. I mean, so that's why it's a good way to do this. Like in real space, for instance, this is an oscillator, not like in a way it's a spring. So it's a spring and it's a mass, so it's just doing this, let's say. So as it is doing this, if you just track the motion of this green dot here, and if you just do the phase space analysis, so this is the phase space, so this is position versus velocity. Velocity is momentum, basically mass times velocity is momentum, so mass is constant here, we are not doing relativity. So in this space, basically this will be a circle. So this entire motion on the phase space is a circle, because this goes up and comes down, goes up and comes down. So the velocity actually it you see it's like the I'm sorry, the position, it goes up and down, up and down. But what happens to the velocity? So when it comes down, its velocity increases, then decreases when it's at the extreme point, because it changes direction then. And then as it changes direction, the velocity again increases, then again decreases as it reaches the extreme point above. So you see, it's like position versus velocity would be a circle. See, position is decreasing and velocity is also decreasing to the mean value. Then again velocity is increasing, position is again increasing. You can just visualize it. There are very lots of good animations also on the internet. So if you're first time, you can take a look. That's very helpful. Now this is the time series of theta. This is the example of let's say a damped oscillator. So this oscillates, but it's damped, so the oscillation decreases until it stops oscillating and settles down. So on the phase space, this would look like this is the phase space, velocity versus position. It would look like a spiral inward, and then it stops at 0, 0, which is the origin. Because this is the velocity, this is the position. So you see theta, the amplitude of theta is basically like in a way the position, and velocity is the frequency in a way. In this case, like how fast is it doing the oscillation? So it keeps rotating, but with smaller and smaller, the radius becomes smaller and smaller, and then it finally stops. So this is a constant oscillator. It's not being damped, neither being forced, and then we get a circle. But since it's being damped here, you get circular pattern, but it spirals inwards. It's no more a perfect circle like this. But here for our model, Kuramoto-type model, we deal with a much simplified phase space, which is the unit circle. So for us, the unit circle is the phase space. We just have a unit circle, and that is our phase space. That's all. Because our phase space is basically one dimensional, because this is the circle, we are only interested in the circumference of the circle, the perimeter, basically, it's not a solid circle. So it's a phase reduced model. So since it's one dimensional phase space, we only need one coordinate to describe the system, and yeah, that's what we do here. To completely describe an oscillator, you only need to know its theta, only need to know its phase. That means you only need to know where it is on the circle, whether it's near 0 or near pi by 2, or like its exact position of the circle. That's enough. You don't need to know anything else. Here you need to know both the velocity and the position. I mean, to plot a point on this space, you need to know both the velocity and the position, otherwise you cannot plot it. But here it's just a one, that's why it's called a phase reduced model. Now the phase of an oscillator 0 to 2 pi, it's a point on the phase space basically, and it completely describes the state at a given time. And each point on the unit circle, which is our phase space, represents an oscillator basically. It can represent an oscillator. I mean, technically it's a continuous, so basically you can have an infinite number of oscillators. There can be infinite number of phases between 0 and 2 pi. It's a continuous, not discrete. Now we look at the fixed points. So what are fixed points? Well, I mean, if the system settles at a fixed point, it's basically the stable points. Now, if the oscillators are phase locked, I already told you that we will assume they are phase locked. By that I mean that the phase difference between all the oscillators is constant. So theta j minus theta is constant for all j. Phase locked doesn't mean that all the oscillators are with the exact same phase. No. So if they're phase locked, then the coupling term is constant. Of course, because this term here, if theta j minus theta I is constant, then sine of theta j minus theta is also constant, and it's a constant for all j. And k is a constant, ki is also constant for a particular oscillator I. So that means this entire term is a constant. So you can forget it. I mean, it matters, but it will not change the dynamics, right? Because it's a constant term. So we ignore the term when solving for the fixed points. So or you can actually more precisely what you can do is that you can define an effective internal frequency by adding these two terms. I mean, you also bring this with omega I. So you call this entire thing as the effective frequency. So you have the effective frequency minus a sine theta I. So basically you group these two terms, since this is a constant and this is also constant for a particular oscillator I. So you group these two terms and you call it the effective frequency, and this is the nonlinear term, nonlinear feedback term. So now this is the simplified equation you have. And okay, if the oscillators are not phase locked, by the way, I mean, then if this term is not constant, then you cannot really say that there are fixed points. Then in general, fixed points do not exist in that case. So now if we want to find the fixed point of this case, where we have assumed that every oscillator is phase locked and the reduced equation is looks like this when the coupling term is constant. So basically fixed point means what? Basically we're asking what happens after a very long time when the system has already stabilized. So when I say the oscillator has already stabilized, that means its phase is no longer changes with time. So d theta I dt is 0 in that case. So we put 0 here. And so we have 0 is omega minus a sine theta. That means omega is a sine theta. If we just do a little bit of algebra, so sine theta becomes omega over a. So theta becomes sine inverse omega over a, and that is a fixed point. So by fixed point, I mean a fixed point on the phase space, on the circle. So that's a theta. It's a value between 0 and 2 pi. And this value of theta is a fixed point because we obtained this value of theta by setting d theta dt is 0. So like I said, sine inverse omega over a is a fixed point. But also, you can have a second fixed point, which is pi minus sine inverse omega over a. Why? Well, think about it. If you have this 0, if you have sine theta is omega over a, so theta, I mean, if you have theta is pi minus sine inverse omega over a, then that also satisfies this equation basically. You can check for yourself. I mean, sine theta is, so in place of theta you put the value of put this value pi minus sine inverse omega over a. So sine pi minus x, let's call it x. Sine pi minus x is, I think, okay, let's figure it out. Sine a minus b is oh, this brings back memories of trigonometry in high school. Sine a minus b is sine a cos b minus cos a sine b, if I am not much mistaken. I think I'm not mistaken. So sine pi minus x is sine pi cos x, and cos pi sine x. Now sine pi is 0, I think. Sine pi is 0, right? Because sine of 180 degrees. So sine pi, okay, I mean, let's just check it out. I'm sorry, let's not waste time. Sine pi minus x. Yeah, so sine pi minus x is sine x. I mean, I knew it was sine x, but I just wanted to figure this out because I mean, I won't bore it with trigonometry. You can figure it out. So sine pi minus x is sine x. That means if you put in place of theta, if you put this value sine inverse omega over a, or if you put pi minus sine inverse omega over a, you get the you still satisfy this equation. That means there can be two fixed points, but one of them is a stable fixed point, the other is an unstable fixed point. So how do you understand what's stable and unstable? Well, you can just find you can also set the second derivative. You take the derivative once more with respect to time. So basically sine ddx of sine x is cos x, so this becomes minus a cos theta I, and this is a constant. So I mean, you can figure it out. If you take the second derivative and do the analysis whether it's positive or negative, you can find which of this is stable and which of this is unstable. But basically you have two fixed points, right? But what happens at omega is and all of this is true when omega is less than a, by the way, because we are assuming omega is less than a, because if omega is greater than a, you can actually have no fixed points. If omega is greater than a, basically I mean, the one way to think about it is that if omega is greater than a, d theta dt will never be 0. I mean, this will in a way keep oscillating. So theta will never, I mean, it's not clear from the equation. I mean, because you cannot forcibly put this to be 0. Just think about the logic. You are putting this 0, that means you are saying that, okay, I want to understand how the system behaves after a long time. But if the system continues to oscillate, if its internal frequency is enough to overpower this damping, then it will continue to oscillate. So even after a very long time, it will not settle down to a fixed point. So then you cannot put d theta dt 0. In that case, you cannot do this analysis. So this is for omega less than a. And what happens at omega equals to, let's say omega is less than a and we have two fixed points. Now we are slightly, I mean, we are increasing omega, and at one point omega hits a. So omega is equal to a right now. So if omega is equal to a, then theta becomes sine inverse 1, because omega is equal to, so omega over a is 1. And sine inverse 1 is pi over 2. So theta becomes pi by 2. And this also becomes pi by 2, because pi minus pi by 2 is pi by 2. So both the fixed points become pi by 2. That means we no longer have two fixed points. For omega less than a, we have two fixed points, but at omega equal to a, we have like a single fixed point, which we call the critical point. Two fixed points merge into one. It's basically a bifurcation. And for omega greater than, we have no fixed points. So basically before you see the two, it's kind of like the two fixed points merge into one, and then that one fixed point also vanishes in a way. It vanishes. Okay. And even in the presence of coupling, okay, I kind of, the notation is a bit confusing, but by omega here I actually mean omega effective, or even if you actually ignore this term, if you just do it with omega, even then you get the similar behavior. Like omega effective is just a constant. I mean, this term is just a constant, right? So it can shift it. These fixed points are only shifted by an effective constant in the presence of coupling, but it doesn't change the dynamics. If we, under the assumption that everything is phase log, that theta j minus theta I is constant. And I mean, if you further assume that everyone has exactly the same phase, then this term actually becomes 0, because all the theta j is equal to theta I, so theta j minus theta I is 0, and sine of 0 is 0. Now let's visualize the phase trajectories and fixed points. So these are some very basic simulations I ran on Python. So this is for omega less than a. This is what we call the locked case, low value of omega. So you see, you have 3 oscillators, and we have kind of traced the path of the oscillator. So one is the green oscillator, one is the yellow. So the yellow and the green are kind of overlapping. So you see, there is the yellow point, this is the yellow arrow, so you cannot see the yellow with your eyes maybe, and this is the blue oscillator. So, and this is this point right over here, the big green point. It's the stable fixed point, and this is the unstable fixed point. And of course, the stable fixed point and the unstable fixed point. So if you have an oscillator which lies in this region, I mean, between the stable and the unstable fixed point, the shorter arc. So this is shorter arc, and this is the longer arc. You see what I mean? And by the way, you cannot say that what if the stable fixed point and the unstable fixed point are diametrically opposite, so then both the arcs become of equal length. Well, that will be possible only if omega is 0, because if omega is 0, then sine inverse 0 is 0. I'm sorry, am I right entirely? Theta is pi by 2, theta, yeah, I think I'm right, because if omega is 0, then basically sine inverse 0 is 0. So theta 1 becomes 0, and theta 2 becomes pi minus 0, which is pi. So then you have one point at, one fixed point at 0, the other fixed point at pi, like 180 degrees, diametrical opposite. But at the same time, omega equals 0 is not a case which we want to consider, because omega equals 0 means the oscillator has no internal frequency in the first place. So it's like not the case of interest. But and for all other cases, you cannot really, I mean, you can have no case, no non-zero omega case where these two fixed points are diametrically opposite. So there will always be a shorter path, I mean the shorter arc and a larger arc. So if the oscillator lies between, in the shorter arc basically, so they will directly converge to the stable fixed point. This is the stable and this is the unstable fixed points. They will directly converge to the stable fixed point. But if the oscillator lies in the longer arc, for instance the blue one starts here, it lies in the longer arc, then basically it takes the longer path. It also, everything basically will always come and settle at the stable fixed point, not the unstable fixed point, but it takes a longer path basically. So if omega less than a, if oscillator is for omega less than a, if oscillator is beyond the unstable fixed point in the longer arc threshold, it takes the longer path and settles at the unstable fixed settles at the stable fixed point, because it cannot, here we're assuming that all the omegas are positive, so they can only rotate, not necessarily positive, but here we're assuming that if someone is here, it cannot cross the unstable fixed point and come here, because if it crosses the unstable, even though it's unstable, it's a fixed point, so then it will get stuck here. So it does this, and if it's here, it directly does this. That's the idea. Otherwise it directly settles at the stable fixed point from the other direction. Now if we have a critical omega, that means right now we have only one fixed point, critical fixed point. Both the fixed points have merged, and right now it's pi over 2. We already discussed, right? Because when at omega equals a, the critical case, theta will be pi over 2. So you see, this is pi over 2, this fixed point. So then all the oscillators just converge to this fixed point. There is only one fixed point, so there is no question of, yeah. But in this case, when omega is greater than a, drifting case, so you see there is no fixed point. The oscillators keep drifting and there is no fixed point. They don't converge, they just keep oscillating. But you see, so these points I have generated just at equal intervals when the oscillator is oscillating. So you see the density of points is higher around this region as compared to here, which means the oscillator kind of slow down when they come here, and the oscillators speed up when they come here. And if you think about it, these were the regions where there, I mean, the fixed points were here. Like the fixed point, you see, when omega was for the same system, when omega was less than a, we had the fixed points, and this was the basically fixed point region, not here. So basically, even when the fixed points have gone after the bifurcation, the system retains some memory of where the fixed point was. I mean, it's pretty easy to see why mathematically. You still have the minimas there, you still have the vector. I mean, you don't have a fixed point anymore, but the system still slows down, the oscillator still slows down on the phase circle when they approach these regions where the fixed point was. And the speed up here is pretty obvious here from the diagram. Yeah, okay, now just like, let's say, small comments on networks. So since we will be modeling coupled oscillators and we'll be doing it on networks, that's a very useful way to study systems, because if I say I have n oscillators and they're connected, so if we really want to interpret our results or get some real results from which we can, draw some conclusions, maybe we cannot, I mean, we have to specify how they are connected and all this stuff. Like, so there are many types of network. For instance, this is a fully connected network where every node is connected to every other node. I mean, all the possible connections exist. For instance, this is connected to this. I mean, all the possible connections, that all the combinations of connections that you can imagine, they exist basically in a fully connected network. And it's huge, actually. It's a huge number, by the way. This is only 20 nodes, 20 blue dots basically, but even you can see. Now this is a random network, loosely connected network, let's say randomly connected network. That means, well, everyone is connected to everyone else. You see, no node is completely free, because if it's completely free, then it's no longer a part of the network. So everyone is connected to everyone else, but randomly. So you just choose the connections and at random, and you do not connect all the connections. For instance, V1 and V13, there is no direct connection between them. There could be, that was a possibility. If it's a fully connected network, then it exists. I mean, see, you see V13, I mean, whatever. If it's a fully connected network, then all the possible connections has to exist. But here, not all possible connections exist, but there is always a path from any node to any other node. Because if any node is completely free, like I said, then it's no longer a part of the network. So even though there is no direct connection between V1 and V13, if you really want, you can go from V1 to V13. You can go from V1 to V8, V8 to V15, V15 to V13. You can go from V1 to V6, V13. It's a very good exercise actually to try to figure out how many, like, what is the average path length, what is the average heating. I mean, in stochastic process, for instance, in Markov chains, we use these kind of ideas like heating time, stopping time, average number of steps, and so on. But yeah, so in fully connected network, we would expect quicker synchronization, because if everyone is connected to everyone else, then, I mean, you really don't have a choice but to behave how everyone else behaves, and you guys all are synchronized. But if it's a random connection, well, it takes time. I mean, information flow between nodes takes time. So let's say this guy is behaving let's say this guy is dancing very vigorously, and this guy is very quiet. So they are connected, but not directly. They are connected, they're very long, they're very far apart. I mean, they are connected through I mean, minimum number of steps, I think, would be one, let's say, two, three, and okay, 4, 5. I don't know, I mean, you can figure out, but there is no direct connection between this and this, between okay, V0 and V3. So if V3 is dancing very very energetically and V0 is quiet, so it will take some time before V0 can slow V3 down, or V3 can pump up V0, if you know what I mean. Because let's say V3 is dancing energetically, so that means V3 will influence V8 and V17. It's direct neighbors, and also here V19 to first of all dance up, and then they will do their nearest neighbors, and it will spread through the network. V17 will do V7 and V13, and V13 can do V0. So it will take some time. But here all the connections exist, so there is a direct connection between V0 and I mean, between any two nodes basically. So for us, these nodes are oscillators, and they are coupled oscillators. So the coupling strength are being modeled by this, let's say, these edges, these red lines, they're the coupling. It's a connected network. So we will study fully connected network where we would expect quicker synchronization. Also loosely connected networks where we will expect slower synchronization. This is a bit technical. I think I'm going to skip this, because I mean, this was actually very important for me when I was doing the simulations, but I have not We will not go dive deep into this in this video, in this presentation. But basically you can have different types of networks. For instance, undirected versus directed network. Like in undirected networks, aij is equal to aji. So basically if there's a connection between 1 and 2, then we assume that the exact same intensity connection exists between 2 and 1. Basically it's symmetric. But in directed networks, it's not like that. It's possible that the connection from 1 to 2 is more strong than the connection from 2 to 1. So in that case, it becomes more complicated because you have to model the connection from 1 to 2 differently from the connection from 2 to 1. So that in that case, aij is not the same as aji. So a is basically called the adjacency matrix. You can model it as a matrix where ij are the elements of the matrix. So for instance, a11 is the first element of the matrix. So it's the connection between 1 and 1. A12 is the second element. A13 and so on. I mean, if you assume that there can exist no self connection. I mean, a or a j cannot exist, then all the diagonal elements basically will become zero. But anyway, but yeah, under controlled conditions, like if there is a strong global connectivity, if the value of k, this capital K, I mean this term, where was it? Yeah, if this is very high, very large number. So for instance, a strong and global connectivity, uneven phase pulling. I mean, in some cases, basically you can have better synchronization if for directed networks. It might sound crazy because in directed networks the effect from 1 to 2 is different from as the effect from 2 to 1. So basically it's uneven. So I mean, we would expect that if it's completely symmetric undirected network, everyone has the same effect of everyone, then we would expect quicker synchronization. That's it's very difficult to say, like make a general statement, because under some controlled conditions, uneven phase pulling, because sometimes it becomes depending on who whether aij is greater than aji or less than aji, and depending on whether the difference phase difference between I and j. This is true. It can happen sometimes. And yeah, what I was saying, so when we are generating networks, we have to specify the number of nodes and the number of connections between the nodes, but this is not enough. If the connections are generated randomly, if it's a fully connected network, you have no room for error. I mean, every connection exists basically. But otherwise, for randomly connected networks, loosely connected networks, we have to ensure all the nodes are part of the network. I mean, if we just specify n and k, for instance, we specify n is 5 and k is 4. So in both these so-called networks, we have 5 nodes, 1 2 3 4 5. Here also we have 5, and we have 4 connections, 1 2 3 4. Here also we have 4, 1 2 3 4. But when we say n equals 5, we actually want a network with 5 nodes, but this is not a network with 5 nodes. This is effectively a network with 4 nodes, because this is not part of the network at all. So it's basically free. This is all right. So this is just an illustration, but this is something we should keep in mind, just to make you understand why I included this diagram, this slide basically. And next, in the end, what we will also do is we will place the oscillators on a lattice. So we all know what a lattice is, right? You have, for instance, you have a grid. It's like a grid like pattern. You have a square lattice, so basically you have a grid. You can have hexagonal lattice. You can have I mean, mathematically there are many different types of lattice which can exist, like many different shapes. You can have square lattice, you can have hexagonal lattice, you can have rectangular, I mean, FCC lattice, for instance. The point is that when we say that we'll be placing the oscillators on a lattice, well, it's good to analyze, because it makes the analysis a bit more rigorous, a bit more easier, because right now you are putting geometric constraints on how the oscillators can be arranged on the lattice. But it's very important to understand this. Here we are not really placing the placing the oscillators. Sorry, what I mean to say is that here the lattice is not in a real 3D space, 3D 2D whatever, but it's not a real space. So it's not like you have a real like grid like structure and on each point you have an oscillator. Because for instance, when the oscillators are oscillating, it's not like the oscillators are oscillating about the lattice point. The oscillators do not move, because the lattice points are fixed and they're only defined by the phase. Oscillations are described only by the phase, but the lattice points are fixed and oscillators remain in the points. So it's a bit difficult to understand. To even it took me a lot of time to get this. Actually, it's not as simple as it sounds, actually, if I'm being very honest. But the oscillators remain in the points. You have a lattice, you have in one, if this lattice point is assigned to oscillator I, this lattice point is assigned to oscillator j, for instance. So oscillator I always remains in lattice point I and j in j. So that doesn't change, it's fixed. And so it's a very wrong visualization. So it's not to think that the oscillator is oscillating about the lattice point, because it's not in a real space, as I told you. Oscillations are being described by the value of theta, by the phase. But this entire point of doing the analysis on this lattice, the entire point of this is just to, I mean, how do I say it? Like like just to put some geometric constraints on the arrangement of the oscillators. But it's a bit more, I should say, difficult than that, and a bit more complicated than that, because it's not like literally a lattice in real space. Because the oscillators are not really fixed in real space, they are oscillating, they're doing this. So it's like, I mean, it depends on the oscillators are maybe doing this, but you are, sorry, they're doing this, maybe for instance they're vibrating, but you are modeling that on a circle. So it's a bit complicated depending on the system you're studying. Here we are not studying any particular system, we're just looking at the mathematics, the general, studying the model in general. And also, yeah, we'll be assuming, I mean, we can assume either free boundary conditions or open boundary conditions. So I mean, both are important and depends on what we want to study. Open boundary conditions makes the job easier, because, for instance, if we have a square here, square lattice, just imagine there are some grids here. So if you have closed boundary conditions, by that I mean periodic boundary conditions. That means, you see what you do. This is one and this is one. So you fold the square into a cylinder. You join the one and the one. By doing this, you ensure that all the points here map to all the points here. Right? That means this ensures that all the points on the lattice are treated in an equal manner. If you have a point here, for instance, it's a square lattice. If you have a point here, it has 4 nearest neighbors in the square lattice. You understand? It's a point in the middle. But if it's a point in the edge, it doesn't have 4 nearest neighbors, because it has some lattice points to the left, but it has nothing to the right. But if we fold this, then this problem is solved, because then to the right you have this, right? But you also have to solve the problem for these two, for these two sides of the squares, but right now they are the circumference of the faces of the cylinder. So you fold the cylinder back onto itself, and you also do this. So just look at this, you can understand. So this is what we call a torus, or this is a toroid basically. It can be constructed from a flat 2D surface by joining its edges. And this is basically what we have. A toroidal lattice is basically, if we enforce periodic boundary conditions, the flat 2D space is basically becomes toroid. It's topologically similar. I mean, if you study modular, if you have studied modular symmetry, something I have studied a few years back, 1 year, 2 years back, actually 1.5 years back, whatever. There is a perfect symmetry between a flat 2D space and this torus, and this kind of structure. Actually, it's a modular symmetry in a way. That's a bit mathematical. It's not really important right now, but yeah. So it's a closed boundary, and choosing closed boundary is a way to, let's say, eliminate edge effects. Hexagonal lattice, yeah, there is a motivation behind studying hexagonal lattice. So because in nature it's often favored in many systems, for instance in biological systems, because it's efficient packing. If you pack hexagon, you have seen the honeycomb structure, right? Without wasting space. I mean, if you have spheres, if you just pack spheres in a very closed, in a small space, there will be some empty regions between the spheres. But if you or even circles in 2 dimensions. But hexagonal lattice, it's the best. It's efficient packing, and also it has a lot of surface area. For instance, if surface area in our case, let's say on 2D, I should say a lot of perimeter, and it's in better contact with neighbors. A square has only 4, let's say 4 sides, 4 edges. Hexagon has 6 edges, so it's in better contact. And at the same time, it's more spread out. I mean, how should I say, it's nearer to a circle than a square, so it has less pointy edges, and that might help, because a square has very pointy edges, triangle even more pointy edges. The angle, so when you're good in a triangle, you're, for instance, you're moving like this, then you do this, so it's a huge change of angle here. But for hexagon, it's like you're 360 by 6, so 60 degrees, right? You see I mean, just it's a very very basic idea actually. So better synchronized oscillations, because you are in better contact with your neighbors. So when we are saying that we are just modeling the oscillators on the hexagonal lattice, that's all I'm saying. So in a hexagonal lattice means the points, the edges of the hexagon, they are the points, the oscillators. And then in that case you have, if you, depends actually, it would be good if I could show some pictures, but okay, let's not dive into, okay, or maybe, anyway. Let me try anyway, because otherwise you won't. Mhm. Hexagonal lattice. Okay. What I'm Yeah. For instance, you look at this picture. I'm sorry. So the lattice is hexagonal, but the lattice. I mean, it depends on you actually. It's okay. It depends on you how you choose to place the points or the oscillators on the lattice. So it's not necessary that you have to place it exactly at the vertices of the hexagon. For instance, these points, blue, green, red, they are the oscillators, let's say, and this is the hexagonal lattice. So how many nearest, and if you say, if you consider these vertices, so you see it has six nearest neighbors in a way, because if you just join, these are all like 1, 2, 3, 4, 5, 6. Let's say you also place oscillators here as well. I mean, just an idea, it depends on how you're modeling it. So you have a more number of nearest neighbors, and you have in a way better connectivity. I mean, compare that with a square lattice, for example, just to give you the idea. Mm-hmm. Yeah, I mean, okay, I mean, maybe this works. So it's a square lattice. So if you're here, you have only four nearest neighbors. 1, 2, 3, and 4. That's all. This is not a nearest neighbor. This is diagonal. So this is the distance is, assuming the side of the square is 1. This distance would be under square root of pi. Sorry, square root of 2. So square root of 2 is greater than 1. So this is not a nearest neighbor. It's a nearby neighbor at best. It's not a nearest neighbor. But in case of hexagonal lattice, you see, if there are oscillators all over here, and if we also choose to place the oscillator here, basically this is the, I think this was there was an this was a HCC, hexagon cubic or something. I mean, in coordination chemistry and stuff, the structure of, we learned, we like face centered cubic, how many different possible. It's not just chemistry, it's actually very good, like in solid state physics actually. But anyway, I forgot actually all the details, but that's not required. But this distance is the shortest distance, and it's same for all the six neighbors. So you have six nearest neighbors in a way. Just to give a basic idea, so you can see why the more number of nearest neighbors, or at least better contact with neighbors, might lead to better synchronization, and also more robust synchronization, because you're, yeah. Now this is a very important and at the same time a little, let's say, counterintuitive idea. That's, can homogeneity sometimes cause faster synchronization? Yeah, emphasis on sometimes. Well, here's a rough analogy. So let's say you have a dilemma. You have both options, like heads and or tails. You toss a coin. So both options are equally appealing. So that's a situation of homogeneity or symmetry, because both are on equal footing. Now you toss a coin. So before tossing the coin, you have like 50-50 options of head and tail, symmetry. But after tossing the coin, you have only one outcome in one toss. You cannot have, like, either you get a head or you get a tail. So that's kind of like breaking the symmetry, asymmetry. In homogeneity, in a way, yeah, you can. This is just an analogy, by the way. Don't take it too literally. But yeah, this helps us to settle to a stable configuration faster. Let's say you go to a supermarket, and you cannot decide whether to buy brand A or brand B, and you are like, no, both are equally good. You're in a dilemma. So you're like, okay, both are equally good, right? So let's toss a coin. If it's head, I'll go with brand A. If it's tails, I'll go with brand B. You toss the coin, you get tails, you go with brand B. So this asymmetry, or let's say whatever, this helps you settle to a stable configuration faster, because you make a choice. Otherwise, you're kind of stuck in a dilemma between A and B. Homogeneity, now in our case, homogeneity means all oscillators have the same phase. I mean, they're already synchronized. Inhomogeneity normally makes synchronization difficult. Of course, I mean, if you're already synchronized, we are already synchronized. What's the point of talking about getting synchronized? But if you're inhomogeneous, then synchronization will be difficult, of course. But at the same time, and in our model, inhomogeneity would correspond to, let's say, random initial phases, random initial frequencies, the way the network is connected, etc. No, but random frequency, in a way, you could think about it like symmetry breaking, because if there is strong coupling, slower oscillators will keep a check on the faster ones, and the faster ones will keep a check on the slower ones. So basically, it's like, as a whole, the phase difference is being maintained at the constant. I told you, synchronization doesn't mean all the phase should be the same, but the phase difference should be constant. And this can accelerate the overall synchronization, because it's, you see what I mean, it's both ways. The faster oscillators are kind of trying to pull the slower oscillators to move a little more fast. At the same time, the slower oscillators are like, no, you guys also slow down a bit. And they're kind of like reaching a middle ground when all the phases become constant. Small heterogeneity also, the speed of synchronization locally. Yeah, if it's heterogeneity but it's very small, then locally it can speed up synchronization, and this might spread globally. Like for instance, we saw this example in the random network, right? How it can spread like this. But of course, if there is extreme inhomogeneity, everybody is different from everybody else, and there is like total randomness, total chaos, then that will not really speed up synchronization. That will slow down, and I mean that will lead to poor synchronization. I'm sorry. Now in this kind of models, we always have a parameter, order parameter. For instance, in this example, if we go back to the beginning, yeah, here R was kind of like the parameter. So here also we can define an order parameter. Order parameter, you cannot take anything randomly. You have to define the parameter in such a way that it gives you some information about the system when it's ordered. I mean, maybe for instance, let's discuss, maybe this will make it more clear. So in the Kuramoto model, we have something called the coherence order parameter. So basically it's the sum of I should say it's the represent the all the phases on the phase space, which is the unit circle in our case, as phase vectors from origin. Let's say we have, this is just an example, let's say we have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So let's say we have 16 oscillators, right? These red dots, and they are just you see the position where they're lying on the unit circle. So these are their phases, their theta I. So I runs from 1 to 16. So we have 16 oscillators, and so how do we find out the coherence order parameter for this particular configuration? It's pretty simple. You just sum, first of all, you from the origin you join all these phases, all these lines. That's what I've done here. You see, one, two, I mean not I took this picture from brilliant.org, but yeah, anyway. So you join this line. So basically you treat them to be vectors starting from the origin, and you calculate the resultant sum of the vector. So yeah, in this case, as you can see, it's symmetric, so the sum is 0. I mean, this vector cancels with this cancels with this. I mean, diametrical opposite, everyone is opposite, and they all cancel out. But for instance, let's say you have only 6 oscillators, and they're this 1 2 3 4 5 6. Let's pretend we don't have all these oscillators. So then the resultant would point upward. The resultant of all this will point upward, like somewhere here. So that means because in that case we would say that we have a coherence order parameter, and the value of the parameter is the, let's say, the magnitude of the vector. So this is a unit circle. So all these vectors, this individually, all these vectors have magnitude of 1. But what you will get depends on how many vectors and their orientations, or the resultant value. But maximum value you can get is 1. Because I mean, if all the oscillators are like perfectly pointing in this direction, I mean in one direction, they're already perfectly synchronized, they already have the same phase and everything, then it's 1. And 0 is like, in this case, it's extremely randomized. All the oscillators are in such a way, arranged in such a way that the coherence order parameter goes to 0. That means basically in such a situation, synchronization would be very difficult. You see, everyone is kind of cancelling everyone out, and they're in opposite spread out, so it's very difficult to synchronize all these oscillators. So this represents all phases on the phase space, a unit circle, as phase vectors from origin, and the resultant vector sum of all phases is the coherence order parameter. It lies between 0, which means complete incoherence here. I mean, see, by the way, synchronization doesn't mean, so for instance here you can see that in this particular snapshot the phase differences are constant. Of course, in a snapshot it will be constant. You cannot see the evolution of the system in a snapshot. But when I say complete incoherence, I mean there is no global preferred phase, because it's completely spread out. But if every oscillator was more or less near here, then we could say that there is a global preference here. So it's like directed in this, like, it's, see what I mean, it's like clustering around here. But here it is not really clustering, it's spread out almost uniformly, uniformly overall through the phase circle. Okay, now we will be looking at the plots of the time series of theta of the phase. Plotting time series of the system of coupled oscillators, how the phase theta evolves over time. So we look at the wrapped time series and also the unwrapped time series. So the unwrapped time series is basically just you let theta evolve with time, and you just plot it. But wrapped time series is when you take into account that you're actually on a circle, and 0 is equivalent to 2 pi. So let's say you are at 0 and you do one rotation, revolution around the circle, and you come back at 0. So it's 2 pi, but that's 2 pi is equivalent to 0. So when we will be plotting the wrapped time series, we use something which we call the modulo n method. It's very standard technique. Modulo, in our case, it's modulo 2 pi method, not n modulo 2 pi. That means every time we reach 2 pi, we force the system back to 0, because 2 pi is equivalent to 0. And this repeats. So this is actually a good way, because this gives us a clearer picture of what's actually happening. easier to read the wrapped time series plots than the unwrapped, basically. And this is the equation, and so these are the parameters. Already discussed all of this. Now the frequency omega is drawn from a normal distribution, so we have to define a normal distribution. We have to define a mean or frequency and a standard deviation. So basically, we define a mean and a standard deviation. Let's say the mean is just as an example. Let's say the mean is 1 and the standard deviation is 0.2. That means you're basically saying that draw all the omega, all the frequencies for all the n oscillators between 0.8 and 1.2, because 1 is the mean and standard deviation is 0.2, so it's plus minus 0.2. That means 1 minus 0.2 is 0.8 and 1 plus 0.2 is 1.2. So all the frequencies should lie between 0.8 and 1.2, but in a normal way, like that, distributed in a normal, as a normal distribution. So there's a peak at 1, basically. And yeah, you can shift the mean, of course. So you can control the what percentage of oscillators have omega less than a and omega greater than, because if you know the value of a. For instance, if you have a is, let's say, 1.1, and if you choose the mean 1 and standard deviation 0.2, so basically you have the omegas between 0.8 and 1.2, and you have a as 1.1. So you see that most of the oscillators have omega less than a, actually, because 0.8 to 1.1, basically, and that's there it's only 1.1 to 1.2. So you can choose whether you want fixed point behavior or this drifting oscillation or continuous oscillation behavior. You can also choose the mean to be 0, because but in that case, remember, in that case, if you choose the mean to be 0, you have both positive values of omega and negative values of omega. If you choose the mean to be 0 and let's say standard deviation to be, let's for instance 0.4, just as an example, then basically it's negative 0.4 to positive 0.4. So you have negative and positive values of omega. And yeah, negative values of omega means the oscillators are oscillating, or let's say rotating on the phase circle in the opposite direction. So for instance, if this is clockwise direction, then they're moving in the anti-clockwise direction, reverse, in the reverse order, basically. So this is the theta versus time plot, and this is the unwrapped phase series. So we have not wrapped it. That's why you see it goes beyond 2 pi. What's the value of 2 pi? Pi is 3.14. So 2 pi is roughly 6.28. But you see this crosses 6.28, 10, 15, 20, and this keeps going. So this is for 30 oscillators, this particular simulation, the plot that you can see. K, I have chosen K to be 1, A to be 0.5, and mean omega is 1 and standard deviation is 0.3. So that means mostly here we don't expect any fixed point behavior. We expect the oscillators to continue oscillating because omega is greater than A. Omega standard deviation is 0.3. That means the minimum value of omega is 1 minus 0.3, which is 0.7, and it is still greater than 0.5. So of course you have oscillation. Now look at this. It appears as if the oscillators. So initially the oscillators are starting from random. So also I'm not sure if I mentioned this, but the value of theta, when we're doing the simulation, we draw theta randomly, uniformly but randomly from 0 and 2 pi. I mean between 0 and 2 pi you choose the initial values of theta, because to solve the differential equation you need to give the system the initial values of theta. So you randomly choose it between 0 and 2 pi. So you see this is between 0 and 2 pi. Roughly you can even visually you can see this is 5, this is 6, this is roughly 6.2, and this is 2 pi basically, and this is 0. So all these points just at time t equals 0, this is time axis, by the way, as you can see this is time. So they're the initial phases, theta, initial values of theta for all the oscillators. Here we have, I think, 30 oscillators. You choose that and then you let the system evolve. Of course, there is some initial randomness, so it's not synchronized, but over time you would expect some synchronization because of the coupling term, and you can see that here there is no synchronization at all, but here slowly things are getting more synchronized here. Not completely, but still you can see it's more or less getting synchronized. Now, why do we see two bands of curves? I mean, why? It looks almost as if this group of oscillators are kind of like we have two different groups of oscillators, like two different clusters. Well, actually that's not true. That's just an optical illusion, because yeah, of course it synchronizes over time a bit. There are still some, like you can see here, it's not, for instance, here the difference between the red and the green curve slightly increases from here to here, as you can see. Just look at here and here, and this is the phase difference basically. On the vertical axis you have theta. So it's not perfectly synchronized yet, because in that case we would expect to be no difference at all. No, I mean we're not saying that we expect all these curves to overlap. No, that's not necessary, but the phase difference should be constant, as I keep saying. Now why is this an optical illusion? Because look at this. What is this? Roughly, you just look at it visually. Roughly this is 15 and this is let's say 20, so this is roughly 22 or 21. So what's the difference between 22 and 15? Well, it's 7. I mean, 21 and 15, it's 6. So roughly, I mean, you can actually check this with the wrapped series, which we will do, but even roughly visually you can understand that the difference between these two bands is 2 pi. The phase difference is 2 pi. And on a circle, the 2 pi means 0, when 2 pi is equivalent to 0. So that means actually this is an optical illusion. This is something which we call a plotting artifact, which arises because we are looking at an unwrapped time series. That's why it's very important to look at the wrapped time series. So actually all the oscillators are synchronized, almost like somewhat synchronized, and they are more or less converging to the same. I mean, they're more or less there is only a single band. There are not two bands. This is an illusion. Because okay, we will come back to this. Yeah. So if you look at this, this is the wrapped time series. You see, this is the modulo 2 pi. Here, why do the wrapped time series look like this? Because see, this is always between 0 and 2 pi. See, this is 6. So this is more or less 6.28, 2 pi. So every time an oscillator and a curve reaches 2 pi, hits 2 pi, you force it back to 0. So that's why this is a vertical line. You pull it back to 0 because you know that 0 is equivalent to 2 pi. So every time you hit there, you come back to 0. Then again, you keep oscillating, and it's very easy to see the synchronization. It's very clear to see the synchronization here because, well, you see, here nothing is synchronized. Everyone is oscillating at their own pace, let's say, but now they're synchronized. And it's very quick synchronization. So they all start with random phases at time t equals 0, but even at time, after a few time steps and at time t equals 8, for instance, they are almost perfectly synchronized. Again, this is for a very small system, so that's why maybe, because here n is only 10, k is 1, a is 0.5, omega is 1. So also omega is greater than a, of course. Okay, now here we have chosen the same omega for all oscillators. So here there is no standard deviation. We are not drawing omega from any distribution. Here omega is 1 for all the oscillators. Okay, that's why we expect faster synchronization. There is no randomness in omega actually. We are not drawing omega from any distribution. So omega is the same for all the oscillators. That means all the oscillators are anyway oscillating on the phase circle at the same speed, but they just have some differences in the phases initially. So that's why that difference quickly dies out because of the coupling term and everything. Okay, let's come back. We were discussing, yeah. So this is an optical illusion because the difference is 2 pi. So on the wrapped time series, you will see that they all synchronize at different times, because this one comes here and this one here, but that means this one comes back to 0, but after maybe after one more revolution. So you are at 0, that means you have 0 revolution. After one revolution, you are at 2 pi. After one more revolution, that means after 2 revolutions, you are at 4 pi. So it depends on the number of revolution, but at the end of the day, you are still ending up at the same point if your difference is 2 pi. So that's why it's a plotting artifact. It's not really like two different bands or two different branches, nothing like that, although it looks like that. Okay, so this was a fully connected network, by the way, and random theta, random omega. Here also we have random phase and random omega, but this is for a loosely connected network. So connection probability p is 0.1. That means 0.1 means 10, right? So that means out of every 100 possible connection, only you randomly choose 10 connections. I'll show you what I mean. Yeah. For instance, here are all the possible connections, but here are only some connections which you have chosen at random. So here they have chosen p 0.2. That means for each node, let's say for this node, there are 100 possible connections, just as an example. Of course, for this node, there are not 100 possible connections. There are, I should say, there are 20 nodes, right? So for this node, there are 19 possible connections, I guess, because we are assuming this node cannot connect back to itself. So there is 1, 2, 3, 4, 5, 6, 7, I mean, all the 19 others. But we are choosing only the probability 0.2 means we are choosing 0.2 times 19. Basically, if we hypothetically assume that for this node there are 100 possible connections, then we will randomly choose only 20 of them if the probability is 0.2, connection probability 0.2. We have chosen 0.1 in this simulation, by the way. So that means it's a very poorly connected network, loosely not all the connections are there. It's a network, but it's very loosely connected. So there, in that case, we would expect poorer synchronization, and that's what we see, because see, this simulation was for 20 time steps. You see here 20. Okay, I'm sorry. Yeah, 20, and this is also for 20 time steps, and we are starting with same everything is same, basically every other parameter is same, but we see there is not very good synchronization. Okay, maybe this is due to again the 2 pi difference. That's fine, but for instance, this green oscillator, it doesn't really it drifts randomly. This difference, you see, it's not really if this is 15, for instance, if this is 15 and this is visually this is somewhere around 8. So 15 and 8 is, I think it's definitely more than 2 pi. And even if you look at this region, they don't really synchronize very well. There's a lot of chaos here. See, here it's more clean synchronization. Okay, now we have identical. Okay, so in this case we have identical omega. So now we are not drawing omega from our normal distribution. So that means we reduce some randomness, and of course we would expect quick and complete synchronization. So if all the frequency were already identical at time t equals 0, then it completely synchronizes at 20 time steps. It's complete overlap between all the phases, as expected. And this is for a fully connected network. That's why it's a bit faster. And again, they all overlap completely. This is just a plotting artifact. This is just single line. It's not two lines. This difference is 2 pi. Same thing we discussed. Now we have the same thing, identical omega random phase, but although we have identical omega this time, we have a loosely connected network, and that's why you see it's not, after 20 time steps, it's not synchronizing very well. I mean, it's still better than this because here omega was random, but it's not synchronizing very well. Not this clean synchronization, right? As you can see, it kind of makes sense. We already discussed this. This is just to give an idea. So if we have everything identical, then there is no point in doing Kuramoto analysis, because if all the omegas are identical and all the phases are identical, then you start synchronized. I mean, you are already synchronized at time t equals 0, and you keep that, you maintain that synchronization. There is no desynchronization, no randomness at all. And yeah, this is for a fully connected network, by the way. Yeah, okay. Okay. I'm sorry. Yeah. Now this is for, okay. So this time you keep omega random. That means you still draw omega from a normal distribution. We have chosen here mean 1 and SD standard deviation 0.2. But this time all the phases are identical. You can see all the phases start the same, like identical, start from 0 here. Here, well, since the phases are initially identical, exactly at time t equals 0, you technically speaking, you don't have any desynchronization. But over time, you see slightly desynchronize. That's because of this randomness in the frequency, randomness of the omega, because some oscillators are drifting faster than the others because of the random omega, and then you have this, it's good. I mean, still overall, the good synchronization is maintained. I mean, overall, it's more or less settles into a fixed phase difference and everything, but yeah, it's not perfect because, I mean, it doesn't, it's not like this, for instance, because there is a randomness in omega. That's it. But yeah, overall, this is the same system, but we run this over a long period of time. So this was for 10 time steps. This is for 50 time steps. You see, it more or less maintains a synchronization. This is a constant phase difference. Not overlap, not all the curves overlap, but you see this phase difference more or less becomes constant, and it keeps oscillating. So this is one oscillation, 0 to 2 pi. Then it again drops. I mean, since this is the wrap time series, so 2 pi means again, so this, and that means basically on the phase circle it looks like this. It's more or less doing this as a cluster, as a single cluster, basically, not really cluster, as a single group. So it's a synchronized group. Now we have everything random omega, random phases, but fully connected network. I mean, okay, this is basically the same thing we started with, random omega, random phases, fully connected network, but now we're looking at the wrap time series instead of the unwrapped. I mean, we already discussed this. Basically, it's easier to see this now because to see I mean, it's easier to avoid those optical illusions, like you have two branches or something here, and it synchronizes significantly over time. You see, just after 10 time steps, already this kind of randomness goes away and it synchronizes a bit. Of course, it doesn't synchronize perfectly because you have random omega, random phase. And if you have identical omega, identical phase, then again, just to show you, I mean, even if you have a loosely connected network, you have the same, it's completely synchronized from time t equals 0 and throughout. Because if you already start with identical omega, identical phase, there is no randomness, no chance to desynchronize. So it doesn't really depend on the number of connections. So for a fully connected network, we had this behavior. For a loosely connected network also we have the same behavior. Doesn't matter if you have identical omega, identical phase. Of course, in that case there is no meaning of studying this anyway, but this is just to show you. And this is the most random we can get. We have random omega, random phase, plus loosely connected network on top of that, the wrap time series. So it's complete chaos, complete mess, very poor synchronization. And over a long period of time, well, you see there is some you can say, we still cannot say that it's completely synchronized, but between some groups of oscillators, more or less the phase difference becomes constant. If you know what I mean, the difference of the phases, the difference between the lines, they more or less become constant, but not completely at the same time. If you just it's repeating, but after some amounts of time, and it's not a very good synchronization. If you just if you look at this figure for a very long time, it's Yeah, because here we went as random as possible. Very loosely connected network, random omega, random phases. Okay, now we do identical omega, identical phases, directed randomly connected. Again, if you have identical omega, identical phases, basically you always have this. Doesn't matter. So here we have directed network, randomly connected. So it's not fully connected, but connections are one way or asymmetric. But yeah, again, it's always synchronized regardless of connections, because you start with identical omega and thetas, omegas and thetas. Here you have identical omega but random phases this time and directed network. So you have this is the wrap time series. And over a very long time, you see, this is very important because it appears very random, but actually you see, even in very short time, you see it's not this kind of randomness. Here you see it's absolutely random. You cannot say even that the phase difference is constant. Here you see, even at short times, this is more or less constant. I mean, there is a constant shift, but the slopes more or less kind of are parallel, if you know what I mean. And over a long time, that's why you see it synchronizes almost perfectly after just 40 time steps. Very good synchronization even for random phases, because omega was identical. That's the most important factor. And also we have directed networks. This is very I mean, that's kind of like, that's why I wanted to mention, I included this in the slides basically. Okay, now we have random omega, random phase, and this time k is less than it. That means the damping is more. K is actually slightly, if I remember correctly, for this simulation, k was not significantly less than it, but yeah, k was slightly less than it. It's almost like in the critical region. K is the strength, network strength, remember, and that is less than the damping strength. That means the system, the synchronization is, we would expect it to be poor, because k is the coupling term which is asking the oscillators, which forces the oscillators to synchronize. But at the same time, if k is very less, I mean, if k is less than a, then that will not really help in synchronization. And a is more, that means it's damping. That means some oscillators are, well, let's see what happens. And this is directed randomly connected network. Okay, fine, whatever. So you see, we get an interesting behavior. This is a wrapped plot, by the way, wrapped time series. You get this brown oscillator. You see this one I'm talking about. This is kind of like the anomaly here, because apart from this, every other oscillator, it goes up to 2 pi and then it comes down. That means basically it's oscillating full circle. But this brown one, it never reaches 2 pi. That means it's not really doing this, it's not oscillating. But at the same time, if it's not oscillating, then we would assume that, okay, maybe there is a fixed point and the brown one should settle at a fixed point. But if it settles at a fixed point, we would expect the curve to look like this. It should become like constant, parallel to the horizontal axis. It should settle at a fixed point. But it's not settling at a fixed point. It's doing up, down, and it's fluctuating. So it's like it's doing, for instance, if this is a circle, it's doing this, it's just it keeps on moving. It's neither settling nor doing full circle rotation, not doing full circle oscillation. So then what is this? See, we run the same system for a longer period of time. This is 20, this is 200. You still see the brown curve never settles. It keeps doing this. It never settles. That means it's neither a fixed point, it's neither it's oscillating full circle. So what is this? Well, we set k equals 0. K is, you see, the connection strength. I am holding hands with, let's say, you. So k is how strongly we are holding hands. If k is 0, that means we stop holding hands. I mean, we drop our hands basically. And now you see this brown curve, it becomes like it's straight. It fixes. It converges to a stable point. That means the brown curve was actually that it belonged to the situation when omega was less than a, and that's true. I mean, that can be possible, maybe, because yeah, I mean, we have chosen omega randomly, so maybe we have chosen the value of a in such a way that some omega could be less than a. So that means if omega is less than a, we had two fixed points, or even if omega is equal to a, we have one fixed point. So the brown curve belongs to the brown oscillator basically. Depending on the initial position, the initial phase where it started, it belonged to that situation, and also depending on its value of omega, that it cannot oscillate, because it has to settle to a fixed point. That's what it does here. But since it's connected to its neighbors through this k, non-zero k, because here we set k equals 0, that's why it's not really being able to converge. So it's more or less oscillating up and down around its, it's oscillating up and down, but that's because of the, it's not oscillating, it's fluctuating up and down because of the effects from its neighbors. But it's not itself an oscillator. It itself doesn't have enough omega to overcome the fixed point, so it itself doesn't do full oscillations. So it's like I am very tired and I'm like almost sleeping. Yeah, it's a good idea. You can think about that this brown oscillator is asleep and the other ones are alive, like they're awake. So let's say I am asleep, but I'm holding hands with two of you, and both of you are dancing very energetically. So if I am awake, then you are dancing, then I might also start dancing. But now I'm asleep. So even if I want, I mean, I don't even know I'm asleep, and you are dancing very energetically. So I will not suddenly start dancing because of that, because I'm asleep. But at the same time, since we are holding hands, since you are moving your bodies very fast and dancing, my body would also start to slightly fluctuate, although not oscillate full circle. I mean, that's what's happening with the brown oscillator basically. Now we do an analysis at critical, I mean, when omega is very close to A. So here we choose identical omega, so the same omega for all the oscillators, but and we choose the value of omega such that it's very close to the value of A. So for this case, we discussed we would have a single critical fixed point. I mean, by the way, I think I should have mentioned this earlier, but it's very important to mention this. When we were doing the fixed point analysis, we assumed that theta j minus theta is constant. Everything was phase locked. I mean, that was just to simplify the analysis, but it's not really the case in these simulations and what we're discussing now in our model, because here we're drawing theta from randomly. I mean, of course, here theta, as you can, I mean, sorry, where, yeah, you can see yourself this theta is these are the values of theta i's different. So theta j minus theta is not always constant here, right? I mean, if you look at it, they're not really I mean to say it's not phase locked. We're not assuming it to be phase locked here. But yeah, anyway, so at the critical, what happens is that the oscillators settle at a critical fixed point. The phase difference between two converging phases is 2 pi, so they're the same phase. Basically, this is again the same optical illusion, plotting artifact. So some oscillators, I mean, all the oscillators actually settle to the fixed point and very fast actually. But at the same time, you see, over a long period of time, it keeps oscillating. I mean, this is not really it's not really converging to a fixed point. It's oscillating. So because here omega is very close to A. Okay, I think I'm sorry. I think I have to check my code here, because I think I chose omega slightly greater than A. I didn't choose omega to be exactly equal to A. That's why I give this symbol instead of equal to. But I chose omega to be actually I can do it right now. Okay, I do it from my second laptop actually, from my because if I mean, please don't mind, because I'm screen sharing or screen recording on this one, and if I have to open my Visual Studio on all my codes, I mean, I have to. I mean, it's nothing like that, but okay. Just give me a second. I'm not pausing, by the way. It will take me a few minutes, few seconds. This was the simulation. It's very difficult to. Yeah, after this, yeah, I have it. Just a second. Yeah, this was the one. Okay, so this is n is 30. There are 30 oscillators. K is 1. Okay, k doesn't matter. A is 0.5. Omega is 0.55. Yeah, I told you. I chose omega to be 0.55. So omega is slightly greater than A. So that's why you see it keeps oscillating. And since omega is identical omega, that's why they synchronize very fast. So okay, I'll just run a simulation right now. In fact, these simulations don't take a lot of time, unlike the Monte Carlo simulations on Ising model and polymers, which I've been doing recently. Trust me, they're a nightmare. They take a lot of time. But these simulations usually don't take a lot of time. So okay, now I choose omega to be exactly equal to A, and I run the same simulation. Let's see what happens. Yeah, of course you got an invalid escape sequence. This time you have okay. Maybe I should do it for 100 time steps. You see. Yes, I show you. I'll show you what happens. And if I do it for instance, let's say if omega is less than A, that's not interesting. That's we already discussed that. Okay, so okay, maybe I have to show you. I have to open this in my, not a problem. It's nothing. Okay, emotions, phase space analysis, RE and yeah, Kuramoto. Okay, I'll just show you. Okay, yeah, I just did this analysis right now. It's on my second laptop, but it's good actually. It's good that we figure things out on the go when I'm presenting. Maybe it takes a bit more time. It's not a, but yeah, it's YouTube. It's not a polished presentation anyway. Uh, but where was I? Yeah, after this. You see, this is the presentation. Okay, so this you see, I just do full screen. Here now is you just look at my code. Here we have chosen omega is np dot ones. Np is just this is basically I'm defining an array of ones and times 0.5. That means all the omegas are 0.5. It's actually good to define an array just because you just keep track of all the n omegas. It's an array of size n because there are n oscillators, which is 30 in this case, I told you. So this time omega is 0.5. Where was I? And a is also 0.5. So omega is exactly equal to a. And in that case, I told you there is one critical fixed point and all the oscillators actually settled at that one critical fixed point. I mean, of course, this is a plotting artifact. This, you see this thing here, this and this, the difference is 2 pi. This is roughly 7.8, let's say, and this is roughly 1.5, let's say. So 1.5 and 7.8, what's that? It's more or less 2 pi, more or less 6.3, 6.28, right? So I mean 1.5 and 7.5 is 6, and 7.8 is 6.3. It's more or less 2 pi difference. You see, this is what you're getting. But it's very important, because if I just slightly increase the omega, let's say I do it 0.52, and let's just see. Let's just see what happens. You see, it's still oscillating. It's still oscillating, and it will keep on oscillating. Once it oscillates, for instance, I do this for time t equals 100. Even if I do this for 500, I hope this won't take a lot of time. No, it won't. It's 2 seconds, 3 seconds. Oh yeah, you see, it will keep on oscillating. But notice this, and this is important. Here the flatter regions, maybe it's better if I just show you with t equals 100. Yes. So notice the flatter regions here are more, longer. So see, from 0, like from here, it's almost like 5, roughly speaking. So from t equals 5 to t equals 40 almost, the oscillator is almost, it moves very slowly. So it's almost a flat region. It moves very slowly. And then suddenly there's a spike here from 40 to, let's say, 45. There's a suddenly spike, and this is very important. And if we do this for an omega which is very large, for instance, let's say omega is 0.7, 0.8, for instance. Now you see, it's not like it's this region is very less. It's between 0 and 20 already. It's oscillating very fast. So this is important. That means you can actually this competition between omega and a. That's what I wanted to show, and that's the most important part actually. And okay, let's get back to the presentation now, I think. So this is oscillating because omega is still slightly greater than a, as I figured out by myself anyway. But it's good that I showed you actually. If you choose omega exactly equal to a, you will get exactly the fixed point. There will be only one critical fixed point in that case. Now the oscillators slow down at these flatter regions. These correspond to the location of the fixed point on the phase circle. We already discussed this actually. Not for this system, because there we ignored we assumed the phase log, but we still discussed similar. Yeah, here. See, the oscillators are slowing down here where the fixed point was there, but when omega was less than a. Just it has some memory of the fixed point, I told you. Similarly, that's what is the flatter regions. The oscillators are slowing down because those were the points corresponding to the fixed points basically. Right now we're in the critical regime, right? And then otherwise we're slightly above the critical regime, but yeah, omega is slightly above the a. And then there's a spike. So the spikes correspond to this thing. So for instance, when you come here, you slow down and you are like very slow, and then once you cross this, you again speed up. So here it's like a spike, just like this. It's a spike. You do this very fast, and then again you slow down. Here again fast, slow down. So that's why the unwrapped time series looks like this. You see. I'm sorry. Yes, you see, that's why it looks like this. Slow down and then again a spike, slow down, spike. And this is very good. This spiking behavior is actually That's why this is a very good model, because this kind of behavior is observed in a lot of regions, a lot of like systems, natural systems, biological systems, for instance, and so on. And for this plot, we actually have omega less than a, and since omega less than a, you can actually see that why there are two fixed points. I mean, you can only see the stable fixed point, but you can I mean, you can actually see both the fixed points. Let's see why. This is fully connected, identical, random, identical omega, random phases, yeah, whatever, blah blah. So of course in this case we have no sustained oscillations, because omega less than a obviously doesn't it's not surprising. So all oscillators collapse to the stable fixed point. Of course this is where they finally collapse. So this is the stable fixed point, roughly around 1 it appears, yeah. Now now how to figure out what's the unstable fixed point? It's very easy actually, because if you know the stable fixed point, if you know sine inverse omega over a, then you can find out pi minus sine inverse omega over a. Remember the other fixed point was just pi minus this. So if this is 1, pi minus 1 is 3.14 minus 1 is roughly 2.14. And what is 2.14, by the way? See, it's here. Oh, wait, am I doing this right? Pi minus, okay. Yeah, so pi minus 1 is 3.14 minus 2.14. I think so, because I would have said it's somewhere around here, because okay, I'm sorry. Yeah, I'm sorry. This is theta. This is theta. So your fixed point was, let me just remind you, because since we're taking a lot of time in this video, but since we're doing this properly, let's do this properly. Theta 1 is sine inverse omega over a, and according to that plot, theta 1 was around 1. Right? Around 1. So that means what is omega over, I mean, what is that angle that if sine inverse something is 1, that is pi by 2 basically, right? So okay, that doesn't make sense. No, I'm sorry, you don't need to think about that, okay? I'm sorry for the confusion. Basically you have this is 1, roughly speaking, this is your theta 1, which is 1, it's a stable fixed point, roughly 1. Theta 2 is pi minus theta 1, basically, which is pi minus 1, which is roughly 2.14. Yeah, it actually makes sense. So it's somewhere here, you see, it's 2.14 is somewhere here. What doesn't make sense is this thing here actually, but maybe okay. But okay, how to understand what's happening here? So these oscillators that directly converge to the stable fixed point are the oscillators that lie, that's why I was wondering, that lie in the smaller arc. I'm sorry, I think it would be better if I give you an just a quick reminder. So this was the stable fixed point, this was the unstable fixed point, and the oscillators that lie in this region, they directly converge to the stable fixed point. And the oscillators that lie beyond this region, they take the longer path. So by longer path, I mean they do the full oscillation, they do the 2 pi oscillation, they take the 2 pi route. Now don't do a direct one-to-one correspondence between the two situations, because that in that case we ignore the synchronization term, but here we have the coupling. I mean, here we are not assuming phase locked. Of course, we start with random phases. But if the oscillators that directly converge to the stable fixed points, these ones, I mean basically these, they are actually the ones which were lying in the smaller arc, if we do the analogy, and the ones which are doing full circle, like they go up to 2 pi, come back, and then they do the stable fixed point, then that is the then they are the, I mean, taking the longer path basically. Okay, now I understand why the confusion arises. Sorry, we cannot really say that the stable fixed point and unstable fixed point, that the equations we got, that omega sine inverse omega over a and pi minus sine inverse omega over a, that will not really work here, because like I said, that was under the assumption that, yeah, okay, so this was under the assumption we got these two fixed points, but here we assumed that this is constant, this is at best 0 or at least constant, but in the simulation we are starting with the random distribution of theta, like so between 0 and 2 pi we're randomly picking theta, so this is not really constant, and in that case we would still expect this kind of behavior of the fixed points, but maybe we don't have exactly this equation. So that means we cannot really say that, okay, since theta 1 is nearly 1, theta 2 should be pi minus 1, should be around 2.14. We cannot say that. It makes sense actually. We cannot say that. This is why it's always important to keep in mind. because if indeed it was pi minus 1, that means it would have been 2.14 somewhere here. That means this wouldn't have made sense, because this directly converges to the fixed point. That means this point lies below the critical, I mean in the smaller arc. So basically visually I would say the second the unstable fixed point is somewhere here, because below this all the points they're doing this directly, and above this they're taking the longer path. So I would say it's somewhere between 3 and 4, I mean somewhere between just somewhere in here, I would say visually. That you can say this visually, this is pretty obvious, but exact value, well, that's a bit more complicated mathematical. Maybe I have to take a look into it. This is, I'm not an expert, of course. Now we'll look at, okay, we already touched upon this, but now let's say we have both positive and negative values of omega. That means oscillators are sliding both clockwise and anti-clockwise on the phase circle. So we will look at systems where oscillators slide both ways. This means omega can take on both positive and negative values. So for instance, we can do this if we choose the mean to be 0, just to avoid bias. Because if mean is 0 and whatever you define the standard deviation, let's say you define standard deviation 0.5, that means it's minus 0.5 to plus 0.5. So this is actually symmetric. You avoid the bias, because that means roughly 50% of the oscillators have a negative value of omega, because minus 0.5 to 0, and roughly the other 50% have the positive value of omega, 0 to 0.5. So we are like symmetric. Random omega, both positive and negative, random phases, fully connected network, unwrapped time series. So n is 30. This is for this simulation. I've just the parameters. 30 oscillators, k is 1, a is 0.2, mean omega is 0. Standard deviation is 0.5. Now, just by looking at this this thing, you can see that the omega runs from minus 0.5 to plus 0.5 distributed normally, and a is slightly positive, 0.2. That means most of the oscillators have actually omega less than a, because from minus 0.5 to 0.2, all those omegas, they are less than a. From 0.2 to 0.5, the omegas, that means you would expect this kind of behavior, that they would settle at a fixed point. We'll see. Since the mean is 0 and standard deviation is 0.5, we have half the oscillators moving in clockwise. I already discussed this. Damping factor is 0.2. It affects all. Yeah, the damping factor affects all the oscillators in the same way, whether they're moving clockwise or anti-clockwise. But yeah, the difference is in the overall percentage of oscillators. So like here, there's a slight bias towards like omega less than a, because more oscillators have omega less than a than omega greater than a. But individually, a does not distinguish between whether the oscillator is moving clockwise or anti-clockwise. That's what I mean. I'll tell you what I mean. I'll show you from the equation. That would be better, I think. Yeah, maybe here. So the value of a is, let's say for instance we have 0.2. So if theta is clockwise or anti-clockwise, that depends on I don't know, the sign of theta. So this is the thing. If theta is negative, I shouldn't say theta is negative. Theta is always positive between 0 and 2 pi. So how do we really say if omega? So if omega is negative or positive, so if omega is negative, then automatically this term, I mean there's a negative contribution to d theta I dt, so this decreases, and then I mean minus a in that case will I mean how should I say? So a is just the damping coefficient. A will always tell the oscillator to slow down. That's what I'm saying. So whether the oscillator is moving clockwise or anti-clockwise doesn't care. A doesn't care about that. This nonlinear feedback term doesn't care about that. Sorry, it will always tell the oscillator to slow down. So whether you're moving like in this way, then you slow down in this direction, or if you're moving in that direction, you slow down in that direction. You just slow down your speed, because it doesn't depend on omega. It depends only on theta, and there's a negative sign. This is like universally negative sign, because theta is always positive, sine theta is positive, a is also a positive constant. So I mean, you see what I mean? If omega is negative, that's a different thing. It's not really true. If omega is negative, it's in the other direction, but that doesn't affect the, I mean this a always treats all the oscillators equally. It's not like the oscillators which are moving clockwise are like, you know, they are more impacted by the damping than, and no, that depends on how you choose the mean omega and a. Like here we see that there is more bias towards omega less than a, but that's not because of, I mean in a way actually, if you think about it, I'm sorry, this statement is not entirely correct, because the damping factor, it affects all oscillators in the same way, true, but at the same time I shouldn't say so, because the damping factor a cannot be 0. I mean if a is 0, then you don't have this term, basically you don't have the a sin theta term, vanishes, and a cannot be negative also. That's the way we define the damping constant. So this A is always positive. That means it does affect I mean, if you allow there to be negative omega, negative oscillators, then it does affect, because then it actually affects, because negative omega definitely have, that's what I was seeing, right, negative omega definitely has a negative effect on d theta dt. So A doesn't really, yeah, I mean, A doesn't affect, it affects, but that is because of omega basically. So, and depending on where you choose, how you choose A, for instance, if you choose A to be 0.1, then you slightly reduce the bias, but I like I said, A can never be 0. So I mean, you get the picture anyway. And right now oscillators can move in both directions, upward and downward, since omega is drawn from a distribution containing both positive and negative values. So in wrapped phase plots, this appears as both positive and negative slopes. So even in wrapped phase plots, so far the wrapped plots we have been looking at, so like this is a wrapped plot, the slope is always positive, so this is a positive slope, and then once you reach 2 pi, you come back to 0. Once you reach 2 pi, you come back to 0, but you don't see this slope, you don't see a negative slope. Don't mind this brown curve, it's not really, I mean, that's due to fluctuation actually. If you want to see the brown curve, then look at this, it's a different case, but it's always the slope is positive, because here we have chosen omega to be positive always, we have not included negative omega, so all the oscillators are moving in the, let's say, this direction, in the same direction basically. But right now here we see that we can have both positive and negative. By the way, this is unwrapped time series, but this is okay, I mean, okay, so this is a wrapped time series, by the way, and here you see, here you have, this is not unwrapped, this is wrapped time series. You still see there is a positive slope, there is also a negative slope, positive and negative, because here omega is both positive and negative. So we'll come back, we'll go back to that. First let's like go step by step. I think we are at slide 53 out of 72. We are just a few more. So in wrapped phase plots, this appears as both positive and negative slopes corresponding to increasing or decreasing phase with time. Negative slope means basically theta versus t has a negative slope, that means d theta dt is negative, so theta is decreasing with time, basically nothing more. I mean, theta cannot be negative, theta is 0 and 2 pi, between 0 and 2 pi. So here we have random omega, but this time both positive and negative, random phase, fully connected network. This is the unwrapped series. So oscillators drift both upward and downward. You see some oscillators drift downward, some oscillators drift upward, because you allow both positive and negative omega. This same situation, but when omega was only positive, I'll just show you the plot. Yeah, this was this. Random omega, random phase, fully connected network, unwrapped. But here you see no oscillator was really moving down. Everyone was moving up. See? But here you now, right now in slide 53, we have this. Yeah, 54. We have this up and down. And over a long time, you see this kind of behavior. Now, this is not really cluster formation, by the way. It might appear that way, but like it's not like there are 3 clusters which are forming, because the difference is 2 pi again. 0, this is 0, roughly this is 0, more or less around 0. This is more or less around 6.28, a little more than, I mean, you can still see what I mean. It's not true cluster formation. This is also 6, 14, 6. This is more or less, let's say 7 and 14. So it's, I mean, maybe, but not distinct clusters, because if you think about it, even if the phase difference is not exactly 2 pi, but very close to 2 pi, that means on the circle, one cluster is here, one so-called this cluster is here, the other cluster is just beside it. So you'll not be able to distinguish at 2 separate clusters in that sense. So basically they all converge to the nearly the same phase. Of course, not exactly the same phase, but nearly the same phase, each arriving after different number of revolutions around the phase circle. So they're not true clusters. And also, yeah, so this is for this same system. I mean, these parameters, the same system, but same initial conditions and parameter values, but we just there is some amount of stochasticity, there is some amount of randomness in the equation, of course, because we are initially we are drawing all these omegas and stuff from random. So I mean, we run the same simulation many number of times, but we can still get slightly different behaviors, because first of all, here there is an added randomness, because omega is both positive and negative. So which omega is what, and the way we are defining, because this is okay, there is no randomness here because the network is fully connected, but at the same time, it depends, because yeah, of course there is some randomness, because omega you are drawing it randomly, even the phase is random, so all the phases are random. So and there is there a fixed point here? Yeah, there can be fixed point, by the way. Of course there can be fixed point, because like I said, most omega less than a is being preferred because of this. So most oscillators have frequency less than a. So there will be fixed point, and since you are choosing the theta randomly, it's a very important interpretation. Since you're choosing the theta randomly as well, so depending on the one particular oscillator, where does it lie on the circle, that's being chosen by theta, but you're choosing it randomly and independently from the way you're choosing its omega. But its omega on the other hand is important, because that will define, that will determine whether it will oscillate or whether it will settle at a fixed point. So that means all of this means that between different runs with the same parameter values, you can have vastly different behavior. Here we have this, but here we have, see, entirely different behavior. These are like kind of two so-called clusters. Again, I don't think, because the difference is more or less 2 pi. But for instance, this one, you see, this particular oscillator, apparently it has omega very high, like near the upper end of omega, so it has omega sufficiently large to overcome damping, and this one is drifting indefinitely. It's possible, it's totally possible, because if omega is, mean omega is 0 but standard deviation is 0.5, so let's say maybe this has an omega of 0.4 or 0.5, which is greater than 0.2 a, so it can oscillate. And we can also get this, because due to the inherent randomness in the system, oscillators with a large magnitude of omega can oscillate in either direction. For instance, if we have an omega of minus 0.5, oh sorry, I remember where I was confusing. So if omega is negative, omega is minus 0.5, then that means omega is negative, that will affect the differential equation, but at the same time we are more interested in the magnitude of omega. So this a, I mean, you see what I mean? Otherwise you couldn't have get. So there is no really bias in that sense. Otherwise you couldn't have you wouldn't have gotten this kind of behavior, because this is negative clearly. So its theta is negative here. Actually, it depends. I mean, it depends how you define, how you see the system, because theta is negative means theta is not really negative. Theta is a number between 0 and 2 pi. But the way to see this is that it's theta versus time. It has a negative slope. That means theta is decreasing with time, which means the phase is decreasing with time. That means it's rotating in the opposite direction. So this one phase is increasing with time, it's rotating in this way, now it's rotating this way. So for instance, this is going from 0 to pi by 2 to pi to 3 pi by 2 and so on, but this one is coming from pi by 2 to 0 and the opposite direction, this one. Makes sense. But that means for to get this oscillation, to get this drifting behavior, it must have a frequency which is greater than the magnitude, the damping coefficient. But at the same time, if you have omega greater than a, well, I mean, since it's in the negative direction, maybe it has something like minus 0.5 or something. I mean, it's definitely, it has a negative value of omega. But if you take the just with the signed value of omega, then negative value of omega can never be greater than a, because of course a is, well, I think the situation, the way to think about this is that in this case, well, d theta dt becomes negative. Yeah, I think this would be the interpretation. I'm sorry, actually I improvised the last few slides, so I'm not prepared, because in this case d theta dt would technically be negative, right? Because theta decreases with time. The way we have constrained theta to be 0 and 2 pi, so the oscillator is moving this way, so theta decreases with time basically, right? So if d theta dt is negative and omega is negative, doesn't really matter, because okay, you just look at this equation. You have, this is negative, this is negative, this is also negative. So in the end it becomes okay, how to here we have sine theta I. Now this term still remains negative, because theta I is still positive. This slope, this gradient is negative. I mean, let's say d theta dt is negative. If you have theta I, that's not negative really. So basically a is 0.2, so this is a negative term. Okay, so you, okay, I think I see this now. So if d theta dt is negative, but theta is decreasing with time, but this you have a negative, so you're adding a negative contribution to this term, right? So you are asking theta to decrease more with time. No, but a is supposed to be doing the damping, right? A is not supposed to. I'll have to look into it actually. Maybe you can think about it as well, because that would be a good exercise. If you're interested in this, and if you have followed the video till so far, that means definitely you're interested. Then you should take a look at this as well. Yeah, because this is kind of crazy, but no, I was getting this. I can check. In fact, I'm looking at the simulations right now. I was getting this behavior actually. But why? That's the question. It's pretty simple. I mean, I'm sure there is nothing wrong or anything, but just I'm not getting the interpretation, the intuition right now. Because it might seem a bit confusing because A is always positive and this time omega is negative. So actually, this term is very important. This was right actually. I was not wrong. Uh, the damping factor is 0.2 and it affects all oscillators in the same way. It doesn't care whether they're moving clockwise or anti-clockwise. If the A will always try to slow down the oscillator in whichever direction you're moving. So that means if magnitude of omega is greater than A, you can oscillate in either direction. So that's the magnitude of omega. This is possible actually. Now why? Why A affects all the oscillators the same way, whether they're moving clockwise or counterclockwise direction? Well, I'm not sure if we can actually understand this that way by doing the sign, whether it's negative or positive from the differential equation itself. But I mean, at the end of the day, what A does is that it's negative A sine theta. So I think, yeah, because here if theta is actually negative, if you're looking, then actually negative A sine theta. So theta becomes negative. So that becomes positive A sine theta. And your I think, yeah, I think that would be the way to look at the situation. Maybe let's go back one last time. So basically, okay, just focus on this portion right now. So basically, since your oscillator is moving in the opposite direction, basically your theta is, yeah, actually it makes sense. Sorry, theta is an angle, right? So if you are moving in this clockwise direction, then that is the, by convention we define that to be negative angle, right? Not positive angle. So that means right now theta is negative, which means this becomes plus A sine theta, because sine negative theta is negative sine theta. So negative negative becomes positive. So this is plus A sine theta. But hey, this time omega is negative, minus omega I. So the sine of d theta dt comes automatically. Yeah, it makes sense. This is emergent. You don't have to, by hand, you don't have to fix that. Oh, since the oscillator is moving in the anti-clockwise direction, that means d theta dt has to be negative. No, this is just as it is. But this time you have minus omega I plus a sine theta. So you can take the negative common and you can say that omega I minus a sine theta, but with a negative sign, whatever. The negative sign becomes, but anyway, the point is, so this becomes negative omega I plus a sine theta. So that means this time since you have your theta is negative, I mean your angle, you're moving in the negative direction. This time this term, nonlinear feedback term, this adds a positive push to you. That means it's asking you to slow down. You see what I'm saying? This time theta is itself negative, but this term is positive. So this term is kind of negative, but this is a positive contribution to a negative term. So this is becoming less negative. Yeah, I see it now. Now I see. So it actually doesn't matter. Actually, it doesn't matter. I'm sorry. When I say that A is 0.2, A doesn't care whether you're moving in the clockwise direction or whether you're moving in the anti-clockwise direction. There is actually no bias. If your mean is 0 and your standard deviation is 0.5, that means there is no bias. 50% oscillators moving clockwise, 50% moving anti-clockwise. And A affects all oscillators in the same way. It's not like A is 0.2, so that means there is a bias towards omega less than A, not like that. I'm sorry. I'm really sorry. 0.2 is the strength of damping, and it will damp all oscillators. It will tell all the oscillators to slow down. Whether you're moving in clockwise or anti-clockwise, just slow down wherever you're moving. If you're moving in clockwise, just slow down in that way, or vice versa. So that's why it's possible to get this as well as this. Yeah. Now we can move on. I'm sorry. Yeah. Last we look at cluster synchronization, and then we will look at the lattice part, and then we can wrap up with this video, with this presentation. So now I know this looked like clusters, but I told you like this is not really distinct cluster. It's very difference is nearly 2 pi. So how can we get the oscillators to form stable clusters? And by clusters, what do we mean by clusters, by the way? So subgroups of oscillators, let's say you have 100 oscillators. Now 30 of them fixed to like more or less settle at fixed point A, 40 of them more or less settle at fixed point B, and the remaining 30 more or less settle at fixed point C. And A, B, and C are not very close, because if they're very close, more or less everyone comes and fixes at exactly the same, almost the same point. So in that case, we will see that there are 3 clusters. The first 30, then the second 30, and also the 40 others. So that's what I mean by clusters. But also, so subgroups of oscillators that either converge to the same or nearby fixed points. Or also, if we say that these out of 100 oscillators, 30 oscillators don't settle at a fixed point, but they collectively they together they oscillate, they keep oscillating together, like they're oscillating but with the same phase together. So that's also clustered. The other let's say 30 and 100, so the other 70 oscillators, they're also oscillating but in a different way, I mean in a different speed, let's say. So the 30 are oscillating with a particular frequency. Let's say 30 oscillators are more or less doing this, the other 70 are more or less doing this, so they are doing it very slowly. So both are oscillating, but yeah, so that means there are two oscillating clusters in a way. So that's what we mean by true clusters, stable clusters. And this should be this should go on, I mean this behavior should be observed long term. Otherwise if it's just like once or twice, I mean it's just it's not transient, like only then we can say that they're stable clusters. You see what I mean? Now, a very good way to do this is that you, instead of drawing omega from a single normal distribution with a mean and a standard deviation, you this time you draw omega from a bimodal distribution. But so let's say you define two normal distribution, one with I mean for this example what I did, I took these parameters are important because not any bimodal distribution will work, by the way. So one distribution I choose means plus 0.9, the other I choose means minus 0.2. So it's important, you cannot choose symmetric means. If you choose plus 0.9 and minus 0.9, then there will be no difference, and then you will not really get true clusters. And standard deviation in both, for both the distributions I chose 0.05, 0.05. So basically what you do is that you define two normal distributions, one is a mean at peak at 0.9 and the other at minus 0.2, and you draw the value of omega equiprobably but randomly from both these distributions, from both these normal distributions. So I use the concatenate function in Python basically when doing the simulation. Concatenate, I mean there may be better ways to do this, but the idea is that yeah, you define two distribution and you draw all the values of your omega, of your frequency, from these two distributions, but they have two different, like peaks at two different places. So this is what I call by a bimodal distribution. I mean this is very recently I was just playing with this, so I included in the presentation, but it's ongoing work, you know. It's for instance, if you're interested and if you have watched the video this far, maybe you can also try like you can we can try with trimodal distribution and many more multimodal distribution basically. If you want the codes, by the way, these codes are not publicly available yet, but if you really want it, you can email me. My email is I mean I on my website, on my YouTube even, it's always publicly available. My email is when everyone knows my email, so you can write me an email if you really want to work on this, if you want the code, or if you want to discuss anything, you can always email me. I can share the code with you. I'm not sharing the code publicly right now for some purposes because this is still ongoing work, but if you want, you can okay, I've not mentioned my email here. Okay, that's crazy. Okay, I just mentioned my email here just so you know if you want to contact me, because if you're watching the video, you can see this. Either you can use this I mean this I would recommend you use this because this is the email I check almost daily. I mean yeah, I do check it daily, not almost, I actually check it daily. So yeah, or you can use this this is my official institutional email, but yeah, long term I don't know, I mean I don't know if I will always be affiliated with Montpellier, so this is like it's not, I mean right now you can use this email also, it's not a problem. I just changed the font a bit so that you this for the email so that you can read it, or you can also use this one but again these two are just like, I mean I would prefer, this is the one I'm mostly on, so yeah. And I always, I mean you can also comment on YouTube, but you know when it's if you really want me to share the code, or if you want to work on this or this kind of thing, then maybe YouTube comment is not the best place. So, and also I cannot really share, like yeah, so sometimes emailing is I mean I prefer emails actually, even over WhatsApp. Yeah, the people who know me, the friends, my friends, and all who have my WhatsApp number, I am more active on emails than on email than on WhatsApp, on Gmail than on WhatsApp actually. That's what my friends say. I mean that's right actually. uh, because in email important stuff happens in email, and in WhatsApp, well, it's mostly distractions. Now yeah, so this is it, bimodal omega distribution. And also this is also important, since we want real clusters now, we don't fix a as a constant. This time we also draw a from a normal distribution. So this is a very complex system. We already, by now, if you have followed the lecture so far, I think you should have a clear idea that this competition between omega and a plays the crucial role in shaping the system. But so far omega was like being drawn from a random distribution, but a single distribution, and a was constant. Right now we are going one step further in both. we are drawing omega from two distributions, and A is also, we are drawing A from a distribution, from a normal distribution this time, with mean plus 0.7 and standard deviation 0.02. So A is not constant, and so that means this is very difficult to analyze. I mean, of course, I didn't analyze this, I just ran simulations, but yeah, it's the system is, I mean, we should appreciate the complexity of the system we are talking about right now. So this simulation, this is for 100 oscillators. It's good to choose a large number of oscillators to actually see the cluster effect. K is 1, random initial phases, randomly connected, also randomly connected network with connection probability 0.1. So everything is random. It's very complex situation. And we see this. Now this is true cluster. You see, this is again they are not really very far away from each other, but at the same time you see the phase difference is not 2 pi. Clearly, this is 0, this is 1. And of course, this is, I've just shown this to you, but I mean, if you play around with the parameters a bit, it's possible to get better clusters. For instance, you get a slightly more spaced out clusters, but again, not 2 pi difference. For instance, one at here. But just to show you, this is a wrapped time series, by the way. This is, you can see obviously. So this is not a unwrapped time series or anything. So what you're seeing here is not an optical illusion. This is actually two different clusters. And they are two stable fixed point clusters, because here everything converges to a stable fixed point. So they are the fixed point clusters. We can also have oscillating clusters, I told you, which we will look at next. So oscillators where the magnitude of omega, yeah, we are looking at the magnitude of omega. Sorry, I mean, I presented this work long time back, and the last few slides on cluster synchronization, I kind of, and these few slides I improvised, so I was not prepared. That's why I got confused in the middle of a few places. Sorry for wasting your time, but yeah. So oscillators with omega, magnitude of omega less than A, they settle directly into the fixed phases. You see, like these ones, I'm talking about this. And the ones which do this, they are the oscillators with omega greater than A. They are also ultimately pulled into log by coupling and heterogeneity. Oh, not really. They have oscillators greater than, I mean, this is either the unstable fixed point case, stable unstable, or actually in this situation is a bit complicated, because very few oscillators would actually have omega greater than A if you think about it, because here we have chosen A to be 0.7, and omega is like, has two means, like two peaks, one at minus 0.2, so everything around minus 0.2 is definitely less than 0.7, and one at plus 0.9, but with the standard deviation. Okay, so no, this class of oscillators will actually have omega greater than A. That's true, that's true. Then it's surprising, because we don't see sustained oscillations. Maybe we do actually. I'll see what can be done about this, because if I'm right, what I would expect is that I would expect to see sustained oscillations, because you see what I'm saying, some omegas are actually have omega greater than A, so why not? So maybe the problem is we are only looking at 10 time steps. Maybe I should run this for more time steps. Okay, let's do it. I mean, what's the problem? This was thank God I have all this copied in my Google Colab, so that I can have everything in my notebook. Okay, because these simulations you can use Google Colab. It's very easy. I mean, doesn't take a lot of time. But for Monte Carlo simulations, for instance, if you don't use VS Studio and other, I mean, if you use Google Colab, you're finished basically. I think it should be somewhere here. What was this? Oh, I was trying something else. Sorry. Basically, I give you a sneak peek into my entire Kuramoto notebook. Basically, yeah, this was the one, right? So I don't know. Maybe let's try time t equals 100. Let's, but no, I don't. Let's see. No, we don't really see oscillations. This one actually, it oscillates. No, we don't really see oscillations. It's more or less everything is. It could be actually. It could be very slow oscillations. Because the reason, if you look at the unwrapped series, actually, it looks to me that it's a very slow oscillation or some of it. But okay. You see, I use the concatenate function. I was just, no. But just wait. Time t equals 1000. Maybe 1000 is a bit too much for my laptop, or let's see what happens. I mean, I was trying many different ways to do to get the cluster synchronization, and well, using the bimodal distribution for omega and also one normal distribution for A, turned to me, it seemed after some trial and error that this was the easiest way to get, easiest way in the sense this was the, with minimal changes in the code and also in the other parts of the system of the equation of the model. This was the minimalistic way. Of course you can, but it's a bit okay, let's see. No, I'll get the result, of course. It's taking a little time, 39 seconds, but I mean, definitely it should be there in a few minutes, at max, in 1 minute, maybe. Let's execute. Okay. Come on, it's 100 oscillators, 1,000 time steps. I can understand it's not a light job. Yeah, okay. Well, it seems there seems to be no oscillations actually. See, this is after 1,000 time steps. You see, no, there seems to be no oscillation. I mean, you see, oh, what happened? Yeah, you see, they're all settled to this fixed point. This is the wrapped series, by the way, so they all settle to two different. Definitely, there are two different clusters, but no, there don't seem to be oscillations, which is, I don't know. Is it really that surprising? Well, because we've chosen omega, but some omega have. Uh-huh. Oh, I'm sorry. I'm sorry. I'm sorry. It's not about omega greater than a or omega. I mean, yeah, for the omegas with plus 0.9, they're definitely greater than 0.7. I mean, the standard deviations are very small. I mean, they cannot really overlap between 0.7 and 0.9 if the standard deviation is just this. But I mean, and for this class of, I mean, for this, it's actually, I don't know. So maybe what there should be. I would expect there should be at least a few oscillators among the 100 oscillators, which have a omega which is greater than a. So those oscillators, I would expect them to oscillate instead of, and they oscillated maybe a few times, but then ultimately they. Okay, I think maybe what you're seeing here is actually indeed, even for when omega is greater than a, they are pulled into log by coupling and heterogeneity. So now, is heterogeneity playing that significant a role? Coupling is fine. I mean, we always have coupling. But is heterogeneity playing such a significant role here? I don't know. Maybe because yeah, of course, this time a is also not a constant. A is being drawn from a distribution as well, but at least a is always positive, and so this a, so that means we are changing a at every time step, of course, but it's like, I mean, it doesn't matter. I mean, a is still, I mean, a doesn't change much actually. It's just I don't know, 0.02 and 0, it's a is almost constant for all practical purposes. I mean, I don't know what would happen if I, for instance, allow this to be 0.3, because if a sigma, if standard deviation of a is 0.3, that means it can 0.7 plus 0.3 is 1, so that means a can seep into the 0.9 well as well. Oh no, I don't need to do this for 1,000, sorry, just stop. 100, I just want to see what changes. I can't wait for 1 minute. This seems to be strong. You see, this one, for instance, it seems to be a strong offset, but I don't see any kind of oscillations, for instance. No, not at all. N is 100, okay. Or is it the effect of just that we have a large number of oscillators? Let's do with 50. Ah, oh my God. This is indeed an eureka moment for me. Oh, okay, okay, okay. This is I get it now. That's what I was saying. It's not okay. Let's go back to the old values. We had sigma 0.02. Okay, fine. The standard deviation of omega. But this time we do n equals 50. Let's go back to the old values. We have some oscillations maybe, but okay, so that means a is okay. If we reduce a, what would happen if we reduce a 0.5, let's say. You see what I did here. So when a is this is I should add this to the slides as well. Thank you. I mean, I should thank myself maybe. Well, anyway, so see here omega is very less, 0.5. That means a lot of oscillators definitely have omega greater than a. I mean, a is very less, 0.5. So you see there is clearly oscillations, and it's kind of cluster. I mean, this is one cluster which is like not doing this, then one cluster is doing this, and initially you have a lot of, let's say, randomness, lot of chaos. uh, but what I'm seeing here is that it's kind of crazy because okay, that's good. That's actually good because that's actually good. Hmm. So I think it's clear to me, because since n was 100, that means we have a large number of oscillators. So, and let's say most oscillators, at least more than half oscillators, were settling to a fixed point. So the ones which were free to oscillate, they were being pulled by the other oscillators, since it's a I think it's a fully connected network, right? It must be, from the sounds of it. Oh no, randomly connected with, oh my god, but still. Well, anyway, uh, was it really a randomly connected network, by the way? It's a random seed. Yeah, it's the see, I defined the adjacency matrix as a with probability connection. Yeah, this was actually randomly connected. It's kind of crazy, because even for a randomly connected network, I mean, so it's not fully connected yet. Still, if we have a large number of oscillators, then they settle. I mean, more or less the system as a whole wants to settle to a fixed point rather than keep oscillating. You see what I'm saying? So that's good actually. Or let's keep the same system. I'll just to show you, let's keep the same system 0.7, but let's reduce it to 30 this time instead of 100. A was 0.7, right? Yes. Don't allow. Yeah, okay. You still don't get oscillations. Okay, let's say n is 20. Yeah, you see, you get oscillations. So for the same parameters, I have not changed anything. I have not changed the value of a standard deviation, mean, omega distribution, nothing. Just change number of oscillators. If there are a few oscillators, then it's easier to keep oscillating, because I have not changed omega a anything, right? But if there are a large number of oscillators, then even if you have a random network with a very less connection probability, it's still more or less, you see what I'm saying? For 100 networks, even a 0.1 connection probability would mean that out of every 100 possible connections, there are 10 connections. And that means, due to the strong connection, everyone will try to pull everyone into kind of like this kind of thing, where you don't have any sustained oscillation. See this? Good, I figured something out new. So sorry for this taking so long for this video, but yeah, thank you. I mean, I'll add this to the slides as well before I upload it to maybe share it or somewhere on my website or something, or ResearchGate. Yeah, if damping constant A is very small, most oscillators will keep oscillating instead of collapsing to a fixed phase. So this is a nonlinear feedback. Of course, if damping constant is small, it will keep oscillating, and this is for only 14 time steps. So if you look at over long time, you see this is like over a long period of time, the wrap dynamics reveal 3 distinct synchronized clusters. So this is one cluster. See this one, this is doing this. This is one cluster. Then the two. This is a rapidly drifting cluster, and the two slowly drifting ones near the top and the bottom. The phase difference between them is not really 2 pi, so I would say they're distinct clusters, but maybe very near to each other on the phase circle, but still distinct clusters. And yeah, they're genuine clusters, not 2 pi artifacts. What did I miss here? We consider the previous scenario, except yeah, this time the same scenario, but we draw A from a normal distribution with mean 0.0 with 0 mean. Okay, this is actually doesn't make sense, because you cannot draw A with mean 0 and standard deviation 0.02, because A cannot be negative. But if you do this, then A becomes minus 0.02. But okay, anyway, we get interesting behavior. Doesn't matter. I mean, we got the. See, this is what I'm saying. Like Kuramoto, this is such a complex system, and there's a lot of richness hiding in it. I just explored it for a few months, like less than few months actually. I mean, not very thoroughly, because this was not my main project. But just by doing this YouTube video, I figured something out just with you guys, just a few minutes back. You see, so there's a lot of rich dynamics hiding in the system, and it's once you have some experience with it, it's almost like if you develop the intuition, the system will speak for you. That's why I was like, initially it didn't click that it was because I have chosen a large number. But in it, just by looking at the plot, I was like, oh my god, I would have expected some oscillations, but why they don't oscillate? Why they settle at a fixed point? So that is the kind of intuition you should have. Just by looking at this, I had that intuition. I mean, I got confused actually. I shouldn't say this intuition, it was more a confusion. But yeah, sometimes confusions help in learning just as much as intuitions. Here, this one for instance, then this one, why was it not settling to a fixed point? So yeah, it's very important. And yeah, you can also more or less force the oscillators to settle to a single cluster by choosing the parameters in such a way. I mean, I'm not spending some more time. It's anyway a very big video, so I think I should stop now. Okay, so this is the same thing, single cluster. This is 20 time steps. This is for 100 time steps. So this oscillates, but as a giant cluster. You see, so the single cluster does not settle at a fixed point. It's an oscillating cluster, as revealed by. So it's always important to look at long-term behavior. Just by looking at this, if you say that, oh, more or less all the oscillators converge to a fixed point, no, they don't. They actually oscillate. And also it's always important to look at the wrap time series, because yeah, like I said, these plotting artifacts do not arise here. It's more difficult to make sense of the unwrapped plot. This is the unwrapped plot for the same situation. Now the last portion, we place the oscillators on toroidal lattice, flat 2D square, and hexagonal, like I said. So here's random omega, random phases, toroidal lattice. So toroidal lattice means I already showed you, just one more time. Okay, just the periodic boundary condition. So you start with a flat square lattice or like a 2D lattice, and this is a toroid. So for a toroidal lattice where we don't have any boundary effects, that since we don't have boundary effects, that means every lattice point is the same. That means we would expect slightly better synchronization if we have a toroidal lattice. And you see this is a 20 cross 20 square lattice, but with periodic boundary condition. That means it's a toroidal lattice and it has 4 nearest neighbor because it's a square lattice. Overall good synchronization. See, except for this red oscillator, after only 15 time steps, this is 14, so this is 15 time steps, we more or less everyone more or less comes closer and synchronizes except this red one. We start with random omega and random phase, and we chose the oscillator placed all over the square lattice. So these are the coordinates. We choose like one at 1 comma 1, one at 5 comma 5, 10 comma 10. 10 comma 10 is like the center of the 20 cross 20 lattice. 1 comma 1 is in this edge. 19 comma 1 is in this edge. 1 comma 19 is the other edge. You see, more or less we try to choose the oscillators more or less distributed around throughout the square lattice. So except the red one is 15 cross 15 comma 15. We more or less, yeah. Now this is actually, I'm still ongoing work. I have not really analyzed this so I don't have a lot of results to show you on the lattice part, and this is very important. So since we discussed so much, I decided to add 3 slides on this. Now this is again random, everything random initially, random omega, random phase, but now we have a flat square lattice. By this I mean open boundary conditions. We don't do the toroid thing, and again 4 nearest neighbor. Poor synchronization, yeah, because see, this is again after 15 time steps. So just if we ignore the red one, we see more or less this is pretty good synchronization, this portion. But here more or less everyone is not so. Just by looking at it, you can understand that this is more steep than this. This is more steep, so the phase difference is not constant. But here the phase difference is almost the yellow and the brown and the violet are more or less parallel. Green is not. I mean, just visually, I'm not making any claims about the lattice part, because like I told, it's ongoing work. And yeah, this is pretty suggestive. This is I can claim this is for hexagonal lattice with open boundary conditions, by the way. So this is more realistic in a way. Much better overall synchronization over the same period of time. See, this is 15. Here you just see after 15 everyone is more or less synchronized. The phase difference is constant. Red and green is overlapping, and these are all like more or less parallel, even if not completely overlapping, but we started randomly. So yeah, this is in a hexagonal lattice, and we chose 5 oscillators. Here we chose 6 oscillators, I think. Yeah, but anyway, that shouldn't change things by a great amount. And you know why? Because in the project which we originally I wanted to explore, but I couldn't due to like anyway lack of time and everything, was cardiac arrhythmias. And also not just cardiac arrhythmias, but studying the contraction dynamics of human heart more generally, because the cardiomyocytes, the human heart cells, they are like they are arranged in a hexagonal manner. That's why hexagonal lattice, and they synchronize. I mean, they kind of they if you treat each heart cell to be an oscillator, then they synchronize because the heart collectively beats. I mean, the heart contracts and then pumps blood collectively. So for that to happen, all the heart cells must be synchronized. So this is a good model to study that. And you see in hexagonal lattice, you actually see better synchronization as compared to this or this. Here is a, okay, I mean, we could skip this just to, yeah. So here we have 50 oscillators. This is a kind of like a thing I built this. Actually, I got a lot of help from my supervisor regarding this one. So me and my supervisor, we wanted to maybe build this here. We can just tweak the parameter, just do the sliders left and right. I mean, this is a screenshot actually, but in the original code you can change the number of oscillators, increase, decrease, whatever. You can change the time, number of time, the time steps, the whether small or big, the resolution basically, the coupling, the damping, the mean omega, the standard omega, and then they will calculate the code. The Python will calculate and give you the value of the coherence order parameter. I already told you the coherence order parameter is basically the resultant sum of all the vectors, like just if you join from the origin to this all the phases. And then so here you have a low value of coupling. The K coupling strength is only 0.5. Well, standard deviation is high in the distribution of omega. That means, yeah, poor synchronization. High standard deviation means omega is more distributed and you have a lot of different omegas, lot of different randomness. And yeah, coherence order parameter is always between 0 and 1. So this is 0.23. It's nearer to 0. I mean, it's overall poor synchronization. Here you have a high value of K, low standard deviation, and in the distribution of omega, so you have a strong synchronization. It's almost 1, 0.99. Yeah. Some applications of this: modeling real world systems with synchronization and feedback, but a better understanding of, see, this nonlinear feedback term was very important. That, so it's basically kind of like I should say marriage between Adler systems and Kuramoto systems, because where was yeah, because this is actually a class of separate class of oscillator. If you just forget the Kuramoto term, this synchronization term, d theta dt is omega minus a sin theta. This is actually called the Adler class of oscillators, because this is an oscillator with random, like oscillator with nonlinear feedback, but it doesn't have the synchronization term. And original Kuramoto model doesn't have the nonlinear feedback term. It's just this. So we kind of combined Adler with you see what I mean? It's kind of like that. And Adler oscillators are very good because in the sense they're a very, very important system to study as well. And they're like maybe they're not as interesting as Kuramoto, but at the same time it's basically, this is kind of like an Adler system, and they have like an oscillator with nonlinear feedback. So this entire nonlinear dynamics is there, but the synchronization part is not there. So in Kuramoto it becomes a bit more complicated. You can define networks and all, how do you want, and then because you have this summation term of a J and all. So what we saw was the simulations and all, it was kind of both. Okay, so that's why it's because very important to model real world systems where you have both synchronization as well as feedback. Better understand feedback means basically the damping. This is Adler, this is Kuramoto in a way. Better understanding of circadian rhythms. These are some like possible applications. Many more possible applications are there, by the way. This is a very general class of, and very, very like like non-trivial class of models actually. So yeah, let me end with it's anyway a pretty long video. Let me end with well, the beauty of physics lies in the extent to which seemingly complex and unrelated phenomena can be explained and correlated through a high level of abstraction by a set of laws which are amazing in their simplicity. Beautiful quote by Melvin Squarch. And thank you for watching. Okay, this was a very, I should apologize for the time I wasted, and because for not being prepared well. I mean, but I actually figured a couple of things out as well with you guys in the video. So anyway, I hope it was helpful. Thank you.